Right. Good morning, everyone. Welcome to the class. Yes, sir. So we would like to implement one Moray system to confirm the statement is correct or not. To confirm the statement is correct or not. Let us see what is that implementation. Right. So let us do same analysis, whatever we have done, writing present state, present input, next state, and output. Then we see state assignment. Then we do implementation. We do implementation. So what we have done here, state diagram we have written, and we have practiced many examples how to write a state diagram for different sequence also. So after that, next step in design process is a state table. What is state table? Present state, present input, next state, and output. So S naught, present input is 0. From S naught, present input is, what is next state? S naught. What is the output? 0. S naught getting 1. Where it is moving? S1, output is 0. S1 getting 0. S1 getting 0. What is next state? S naught, output is 0. S1 getting 1. It is S2, output is 0. S2 getting 0. S3 output is 0. S2 getting 1. It is again S2 output is 0. Remember this, some of you may be getting it out. S2 0, next state is S3, output is 1. No, don't say output with respect to next state. Next state we are going to see after next clock edge occurrence. So at this instant of time, input is 0 means that means the system is in this state only. So now input is applied 0 at this clock cycle. We are applying a 0 at next clock at the occurrence. State is going to be changed. But in this clock cycle, the state is S2. The output is 0 only. Remember this. For S2 0, you may be getting a confusion. S2 0, it is moving to S3. It is moving to S3. But output is not changing now in this cycle. Output will be changing after reaching to S3 state. S3 state you are going to see after next clock edge occurrence. After next clock edge occurrence only output is 1. In this clock cycle, output will be 0 only. So instead of this blindly, we can follow that output is defined based on present state only. So here it is state is deciding what is the output in this cycle. The next state we are going to see after clock edge occurrence. After state is changing, output is becoming 1. But in this cycle, still the state is S2 only. Now, if it is S3, if it is S3, input is 0, input is 0. What is the next state? S naught. Output is now 1 because here S3 is deciding. Now S3 getting 1. What is the next state? S1, output is 1. Output is 1. Output is 1. Now, what is the next step? State assignment. As it is 4 states, 2 flip-flops is sufficient. Let me say Q1, Q0, 0, 0 is assigned to S0, 0, 1 is assigned to S1, 1, 0 is assigned to S2, 1, 1 is assigned to S3. These are S0, S1, S2, S3. So I'm using, what is it here? 4 states. 4 states. So S naught, S1, S2, S3. S1, S naught, S1, S2, S3, right? Now, now what is the next step? Implementation. Implementation. Let us see implementation. Let us see implementation. Ujjwal, that's what I've been saying, that you think generally. So S3 to S0, output is 1. S3 to S0, output is 1. So don't say with respect to this, say with respect to this. So in this cycle, system is in S3 state, right? Then output should be 1 because the output is depending on only on state, output is not depending on input. So at this moment, what is the state? S3. So S0 we are going to see after next clock edge occurrence. Next state, next state. But here S3 is deciding what is the output. So blindly remember that based on present state, we are deciding the outputs. We are deciding the output. Visual. That's what I mentioned. Same thing I'm repeating. So right now, let us do implementation. Present state, present input, next state, flip-flop inputs and output. Let me say this Q1, Q0, X, Q1, Q0. Let me use D flip-flop. You wish. You can use JK, you can use SR. You know how to design the system now. So you know how to write excitation tables of each and every flip-flop, and you can say what is that input expression by using K map. We can complete that. So again, Z. So one by one. S0, 0, S0, 0, right? 0, 0, X is 0. What is next state? S0, 0, 0. Inputs required 0, 0. Output is 0. S0 getting 1. What is next state? S1, 0, 1. I'm writing directly. You can check it in the previous slide. So what will be the inputs? 0, 1 and output is 0. Now S1 getting a 0. Where it is moving? S0, 0, 0. Inputs is 0, 0. Output is 0. Now S1 getting a 1. What is the state? S2, which is a 1, 0. Inputs is 1, 0. And output is 0. And S2, 1, 0. 1, 0. Then what is it here? Present input is 0. Then what is the next data? It is S3, 1, 1. And inputs required 1, 1. Output is 0. Output is 0. Now S2, S2 getting 1. S2 getting 1. What is the next data? It is going to S2. S2 getting 1 is again S2. Right? Inputs is 1, 0. Output is 0. Now S3 means 1, 1. Input is 0. Next state is what? S0, 0, 0. Inputs is 0, 0. Output is 1. S3, yes, getting 1, getting 1. What is the next state? It is S1, 0, 1. And inputs required is 0, 1. Output is 1. Output is 1. For Q1, Q0, X, if I give input combination of 0, 1, 2, 3, 4, 5, 6, 7. 6, 7. Now, what is the expression for D1? Sigma M of, what we can use? Again, 3, 4, 5. And D1 is equals to sigma M of 1, 4, 7. Z is equals to sigma M of 6 and 7. Already we know these expressions. I'm not writing again expressions that you can do. Only difference is Z equals to what? Q1, Q0, X bar plus Q1, Q0, X. If I take common Q1, Q0, X bar plus X is 1. So it is Q1, Q0. By this time, you might have understood what is it here. Output Z is depending on state Q1, Q0 only. It is not depending on X input. These are Moore systems. These are Moore systems. We are getting a combinational block. Q1, Q0, X. Here also Q1, Q0, X. But what about Z? Only Q1, Q0. Only Q1, Q0. Only Q1, Q0. Venkat Brahma Reddy. What I have written? Both D1 where Brahma Reddy. In minimal X. Okay, right. Okay. Yes, thank you, thank you. I've been looking into this where I've done right. Yes. So in this, you have observed what is that here? Output is depending on only state Q1, Q0. Output is not depending on input X. These are Moore systems. These are Moore systems. Already we have discussed the why not taken. Triveni, please expand your question. I'm not able to understand. Why not taken three present states, sir? Why only take Q1 and Q2 only? See, what I've written is here a combination circuit I'm writing. I'm not writing it as a logic circuit. I'm not saying only Q1, Q0, X here. There is a combination circuit which is using inputs Q1, Q0, X. Q1, Q0, X. Triveni, I'm not saying it is a logic circuit with only Q1, Q0, and X. It is not indicator. Please understand this. It is not indicator. Simply, I'm writing a combinational circuit here. A comb and a comb, which is using Q1, Q0 as inputs. Q1, Q0, X as an input. Triveni. Yes. Based on this, we can write expression. We are going to implement that circuit. That is not required for us at this moment. I'm writing simply a combinational circuit. I'm writing simply a combinational circuit. So what we have observed till now is in Moore systems, what we have observed, it requires one state is extra. It requires state is extra compared to Mealy systems. What we have observed here, it requires state is extra. Am I right? For 110, there it is only three states. Yes, I will talk about that, Bhaskar. Please wait. Yes, okay, I understood. Right. So, how many states are there? Four states. To differentiate four states, how many flip-flops required? Minimum, that is only two flip-flops. Reason to consider only Q1, Q0, two flip-flops. Why can't we use three flip-flops if you are having such doubts? Right? That we go with minimum number of flip-flops only. You can design with three or four or whatever it be, not a problem. But have done an optimal implementation by observing number of states is four. To differentiate four states, minimum number of flip-flops required is two. That is the reason I'm going with the two flip-flops. Triveni, I'm optimizing number of flip-flops. Number of flip-flops. Yeah, very good theory questions we have been getting in ESC, especially, right? So, yes, yes, Sai Kumar, that's what we are using formula, right? Capital N is number of states. If N is number of flip-flops, capital N must be less than or equals to 2 power N. The minimum N value can satisfy this equation is minimum number of flip-flops. The minimum N value can satisfy this equation is minimum number of flip-flops, right? That's what we have been discussing, right? So with that only we are proceeding here. So what is that here? The differences, if you are observing correctly, very good theory questions they have been framing in ESC objective questions, sir. Mealy and Moore differences, sir. What is Mealy? Output depends on state as well as inputs. Output depends on state as well as inputs. output depends on state only. Less number of states requires more number of states. And if you are observing, whatever the changes are there, inputs, those can change output directly. Whatever the changes are there on inputs, can change output immediately. In which state? In which systems? Mealy systems. So output is asynchronously affected by inputs. Am I right? Output is asynchronous to input. Output is asynchronous. Why? Is it responding to the input synchronously? No. So output is depending on X input directly. Whatever the changes are there in X, so those are affecting the output. Output is asynchronous to input. But here, even though changes are there in input, those changes are affected the state and as well as output at next clock at the current zone. That is synchronously it is affecting. Am I right? Output is synchronous to input. I hope you are following. As the changes are affecting, right, easily it is unstable. Comparatively, it is having more stability. More stable. So comparatively, what is it here? Compared to Murray system, these are unstable and these are stable. These are stable. So these can be the differences which we need to observe. So what is it here? Output depends on state as well as inputs in Mealy systems. Output depends on, what is it here? State only. State only is a Murray system. Right. These are major differences we need to observe. Wherever the changes are there in inputs, those can change the output in Mealy. But Murray output is changing at next clock at the occurrence only. Yes, Brahmanand. If you want to change the output of a Murray system, you have to wait for next clock at the occurrence only. Even though there are changes in the input here in this clock cycle, so it is not responding those input changes immediately. That's what we are observing, right? Whatever the changes are there in input, even though there are changes in the input X, those can change the state after next clock at the occurrence only. Until that output is not changing. So if I want to change the output, you have to wait for next clock at the occurrence. In this cycle, some output is there. I want to get another output. That means if I change X here, it cannot change the output. It has to change the state at next clock at the occurrence, synchronously with clock. At next clock at the occurrence only, we can change the output. Ramanand Reddy. So output, if you are observing, output is affecting me. For example, X is getting a noise. X is getting a noise, external input. Then obviously output is getting affected, right? Whatever the noise is there on X, right, that can affect the output. That means unstable, right? But coming to Murray systems, it is capturing what is there on X at clock at the occurrence only, right? It is stable, right? Understand correct? Puja. So in this Mealy systems, output is directly depending on X. Then obviously what is happening? If there are any variations in X input, that can change the output immediately. But in reality, that is not required to change the output according to the variations or disturbances on X. In Mealy system, it can change the output, but Murray, it is not possible. In Murray, it is not possible. Am I clear? In Murray, it is not possible. What is happening here? output is getting affected by input at next clock edge occurrence. What is there on X will be captured at clock edge occurrence only. Is it capturing whatever is there on X in the cycle? No. Pooja, yes, thank you. Thank you for understanding. Right. Okay. These are merely Murray systems. The next thing is a state minimization. We should understand a state minimization. Frequently, we have been getting questions. State minimization. What is it here? Unknowingly, you might have defined some states as extra while defining FSM. So when we have multiple inputs, more number of inputs and more number of states, unknowingly you might be defining one state is extra. Instead of going back, sometimes instead of going back, you may be observing, you may be taking another state extra. Right, to understand correctly. According to the functionality, right, it may be required to go back to the one of the state which is already defined, but unknowingly, if you are not observing, it has to go back to the next, or it has to go back to the previous, you are defining another state extra. All those states are extra. So you may be defining the states unknowingly extra. That extra state must be eliminated. That is called state minimization. State minimization. So it may be given state diagram or state table. It may be given state diagram or state table. Then what should we do is a simple thing. Even though state diagram is given, we need to write state table. Even though state diagram is given, write state table is important thing. Once again, what is here? Even though state diagram is given, first thing is you need to write a state table. After writing state table, what you are observing, listen carefully. So present state, next state for X equal to 0, X equal. The way we need to write state table, I'm explaining. Output for X equal to 0, X equals to 1. From a given state diagram, we can write this, right? For each and every present state, what is next state for X equal to 0, X equals to 1. Let me write two different columns for X equal to 0, X equals to 1, next state. And output, also, we are writing two columns. One is X equal to 0 output, X equals to 1 output. Then, for example, you are writing like this. S0, S1, S2, S3, and so on. Or you can use ABCD also, or you can use PQRS also. No need to use S0, S1, S2, S3 only. Your wish. You can use that ABCD also. You can use PQRS also. Not a problem. So let me take it is like this. S1, S2, S0, S2, and here it is. Let me take S1. S3 and S1, S3, for example. Let me take outputs are like this 0, 1, 0, 1, 0, 1, 0, 1, and here it is 1, 0, 1. It is like this. For example, the state table is given like this. State table is given like this. Then what you are observing, let us see. What we are observing in this, please understand correctly. So where is the possibility of extra state or redundant state, sir? So one state is having behavior of another state. One state is having behavior of another state. It is same as another state. Then we can merge those two states, sir. Simple concept is if two or more than two states are having same behavior. If two or more than two states are having same behavior, then what we are saying? Merge those states into one state. Behavior is same. What do you mean by behavior is same? I hope am I audible? My voice is a bit low today because of some throat infection. We have been taking continuously classes. I may be shouting more because of we don't have a mic. We have a laptop mic only, right? So am I audible? Please respond. Is it clear? My voice is a bit low today, right? Thank you. Thank you for your response. Right. So what I've been mentioning is two or more than two states are behaving same. Two or more than two states are behaving same. Then we can merge those states. What do you mean by behaving same? Next state for X equal to 0, next state for X equals to 1, matching for those two states. Output for X equal to 0, output for X equals to 1 also matching for those two states. So for two or more than two states, behavior is same. Is nothing but next state for x equal to 0, next state for x equals to 1 matching. Output for x equal to 0, output for x equals to 1 also matching. These are the important things we need to observe. So if you are observing here, S2 state and S3 state are having same properties. Then instead of S2 and S3 separately, we can eliminate one of these. Because see, S1, S3, S1, S3. Now, what is it here? 1, 0, 1, 0. So all these are matching. When all these are matching, then why do I need these two states? One can be merged. And then what we can say, wherever S3 is there, wherever S3 is there, there I use now S2. So by eliminating this S3 state or S2 state, your wish, anyone. So if I remove that S3 state, now wherever S3 is there, there I can write S2. There I can write S2. Modification. Is modification. Now, what else we are observing here is check it correct. See, when these two are observed, so these are S2, these are S1, S0, and these outputs are 0, 1, 0, 1. Take it correctly. These outputs are 0, 1, these outputs are 0, 1. Here it is matching. First thing is outputs must be matching. Instead of observing states, first think about outputs are same or not. If outputs are same, we can think of the states. Yes, here outputs were same, as states were same, we are merging these two. So this can be removed. That's what we have done. And after that, what we are saying? So wherever S3 is there, there we are writing S2, replace it. And after that, what is it here? These two are having same outputs, 0, 1, 0, 1. So now S1, S2, S0, S2. S1, S2, S0, S2. And these two are same, and these two are same, these two are same. Only difference is these two. The difference is also if you are observing only present states. Very simple thing. What is it here? When these two are same, these two are same, these two are same. Only difference is this. That difference is also only present state. Then also we can merge. What is it here? When these two S1, S0 are same, these two are becoming same. When these two are same, these two are same. Then again these two are also having same properties. Check it correctly. As outputs are matching, and one of the next state for x equals to 1 or x equals to 0 also matching, and one of the next state is different. The difference is also present state. Then also we can merge. So I can remove this state. Wherever S1 is there, there we use now S0. There we use now S0. Right? So what is it now? Modified present state, next state, output. X equal to 0, x equals to 1. And x equal to 0, x equals to 1. Now what is it here? S0, and next it is S0 and S2, it is 0, 1. And here S2, S0 and S2, and here it is 1, 0. And if you are observing, these two are also having same, right? But outputs are not same. We cannot merge. So to merge, outputs also must be same. So how many states are there after minimization? 2 states are there. 2 states are there. What are the 2 rules we have observed? Let us see here. So in the table, if entire properties of states are same, what do you mean by properties? Next state for x equal to 0, next state for x equals to 1. Output for x equal to 0, output for x equals to 1. And for multiple states, then all those states can be merged. All those states can be merged. The other possibility is, let me see here. If I say that A, B, and here it is B, A, and C, C, 0, 1, 0, 1. In this case also we can merge. What is that here? Everything is matching except these two. Except these two, the difference is also present states only. The other possibility, let me take that like a C, D, and here it is A, D, and A, C, 1, 0, 1, 0. This also can be merged. Here, this is same and these are same. The difference is also this much only. So again, these two also can be possibilities. One is a row, entire row is matching. Second thing is everything is matching except next state for x equal to 0 or x equals to 1 is different. That difference is also based on the present states only. So BA, AB. here DC CD. Then we can merge. Then we can merge. Entire row is matching. Then also we can merge. These are the possibilities of merging states. Very simple techniques. So to minimize. For conventional ESC, we can discuss some more points. What is it here? Partitioning method. If they are mentioning clearly, use partitioning method, we have to use partitioning method only. That I discuss later for conventional ESC. Until that, please hold on. So at this moment for objective exam, this method is sufficient. This method is sufficient. So they may be saying clearly, use what is it here? Partitioning method. There we use partitioning method that we do in conventional ESC after completion of this objective. Right, fine. So at this moment, once again, I'm explaining state minimization. One thing is a merging of the states when all the properties are same for two or more than two states. Second property is so it may be matching everything except next state of x equal to 0 or next state of x equals to 1. The difference is also present states only. Then we can merge. It may be for x equal to 0, it is differing. It may be differing for x equals to 1 also. It may be differing only for x equal to 0 or only for x equals to 1. Everything is matching. That difference is also based on the present states only. Then we can merge those. We can merge those. Now let us see what is the possibility of minimization with examples. Please understand these steps. Now we can proceed. We can proceed. Right. To minimization. Let me take one example. Right. So present state. It may be given state diagram also, but you need to write this x equal to 0, x equals to 1, output z for x equal to 0, for x equals to 1. So let me use A, B. This is a general example I've been using to explain E, D, and F, D, E, B, F, B, C, B, C, F, C, F, B, C. And here it is 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0. Do state minimization. Please complete this state minimization. Very simple thing. Listen carefully. So question is how many states are redundant or how many states after yes. Yes, Ujjwal, correct. So what I can do, just think of these two or sorry, these three or these three. There may be possibility for merging these only. So I'm using two different symbols. These three should be observed because outputs is same, and these three should be observed. These three should be observed. Then what is it here? If you are observing, is there any possibility for merging any of the states? In the first step, yes. If you are observing here, FD, FB, and 0, 0, 0, 0. Observe correctly. FD, FB, 0, 0, 0, 0, and here it is BD. So what we are observing here, F and F it is common. See, these two, B and D, if you are observing, right, FD, FD, output is same. FD, FB, F is same, but here DB, that means these two can be merged. These two can be merged. Any doubt in that? Is it clear? These two can be merged. So one can be removed from this. Which one you want to remove? Your wish. But I'm removing here D. Let me remove D. Why we are removing also, I explained right clearly. Right. Now, wherever D is there, I need to use now B, modification. Wherever D is there I need to use D. Then what else is there? You are observing these two. Any possibility for merging? No, not possible. Next, you are observing 0, 1 output. 0, 1, 0, 1, 0, 1. And 0, 1, here it is 0, 1. And here it is EB, here it is EB. Yes, one can be removed. One can be removed from this. If I remove this, wherever C is there I have to write, what is that? There I have to write A. Wherever C is there I have to write A. I have to write A. No? Then it can be removed. It can be removed. Now, so if you are observing 0, 1, 0, 1, is there any possibility for merging? Not possible. 0, 0, 0, 0. Is there any possibility for merging? No. So finally, what is it here? There is no possibility for further elimination of states. So how many states are remaining? Only 4 states. How many states are redundant? 2 states are redundant. Simple thing. So as I mentioned, 3 rules. The 3 rules are very useful. You apply that, you can eliminate extra states or redundant states. If you are eliminating that, the remaining are actual states. And whichever the states are eliminated, those are redundant. So they may be asking how many states are redundant, how many states are there after minimization. By giving a state table or by giving a state diagram, they may be asking how many states are redundant, how many states are there after minimization. This type of question. How many states are there after minimization? 4 states. How many states are redundant? 2 states. Right, right. There was a question in a previous GATE exam, EC GATE exam. I'm not giving that entire, like almost to write here, it may be taking 5 or 6 pages. What is the information given is, there is a clock with t equals to 5 nanoseconds. I have to design a traffic signal which is red is on 75 seconds, right? Then yellow must be on for 5 seconds, and green is on for 70 seconds. The values may be changing, but mostly these 3 only. I am doubting that the R and G may be different. Not a problem. So what is it here? Red must be on for 75 seconds, and yellow must be on for 5 seconds. Green must be on 70 seconds. So available information is only clock with 5 nanoseconds. Sorry, 5 seconds, not 5 nanoseconds. These are 5 seconds. So a clock is available. Simply a clock is available with the 5 seconds. 5 seconds. Then how many flip-flops required to design this FSM? How many flip-flops required to design this FSM? Unfortunately, here we don't have any input to consider. Only clock is there, and we need to design simply a system which is going through these possibilities. Then what can I do? What can I do? Simple thing. How many clock cycles it has to count? Simple thing, simple question. How many clock cycles total it has to count? Because here it is 15 clock cycles. And here it is 1 clock cycle. And here it is 14 clock cycles. That means finally, how many clock cycles total it has to count? 30 clock cycles it has to count. To count 30 clock cycles in each cycle, I need to design a mod 30 counter, right? Mod 30 counter. To get 30 states, how many minimum number of flip-flop required? That is a question. Looks like very lengthy question, but people have got confused. But nothing great in that very simple question. Very simple question. So thing is, 30 clock cycles has to count in each cycle. 30 clock cycles it has to count in each cycle. That means in each cycle, how many states it must be going through? 30 states. That's it. 30 different states is required. 30 different states is required. So how many minimum number of flip-flops required? How many? 5 flip-flops, because n is equals to 30. 30 must be less than or equals to power n. What is the minimum n value? 30 less than or equals to power 5. 30 less than or equals to 32. Yes, it is satisfying. Minimum n value is 5. Minimum n value is 5. Very simple question. Very simple question. Also, good question to confuse. Very good. That's it. Very simple. Very simple. Any questions in these? Any questions in these? And I'm suggesting you to write a state diagram for 11011 More. One is overlapping, other one is non-overlapping. Not now, later. Practice this. If you find any doubt, please let me know. Please let me know if you have any doubts. Yes, Dinesh. Yes. Yes, Bhaskar. Nothing great in that first slide. Simply writing a table. This what only. Yes, I'm doing Shubham. I'm doing Shubham. No worry. Right. Again, you want me to explain? Right. I will give you one classroom practice question is there. I will give you some more also later. Hold on. So some people are requesting to explain once again about this data. Let me take once again. Let me take once again. So what we have here is a present state, next state for x equal to 0, x equals to 1. Output for x equal to 0, x equals to 1. So let me write here A, B, C, D, E, and F. And if I write next it's E, D, E, D, next E of D, right? E, B, E, B, and E of B. And what do we have here? C, F, then B, C, then outputs is 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0. So listen carefully, and everyone can do this. To observe whether they are redundant or not, first thing is output must matching. So I'm marking these are having same outputs first thing. Then these three are having same outputs. I can look into these three first, right? Or these three. So in these, which one is having redundancy, we can observe. If you're observing A, C, E may not be getting clarity immediately, right? Now, if we are observing here B, D, F, B, D, F, in that, if you are observing outputs is same B, D, F, and here what we are observing F, D, F, B, F, D, F, B, outputs are same. The difference is what? Here D, B, that is also same as present state. That means these two can be merged. Observation, these two can be merged. Anyone has any doubts? These two can be merged. That means I'm removing D. I'm removing D. Then what can be the states? Let us see. Present state, next state, and output. So x equal to 0, x equals to 1, x equal to 0, x equals to 1. Then what we can write here? A. We are writing wherever D is there, there we need to write wherever D is there, there we need to write B. So E, B, then here it is 0, 1. I'm removing D. I'm removing D. As I'm removing D, wherever D is there, there I'm writing B because these two are same. Now B, F, again here D is there, in place of D it is B. Then it is 0, 0. And what about here C? What is it here? E, B, and 0, 1, 0, 1. And D is not there. Now it is E. For E, C, F, what is it here? 0, 1. And again F, B, C, F, B, C. Here it is what is it? 0, 0. Once again, we need to look into same outputs. 0, 0 is there, 0, 0 is there. FB, BC. No possibility for merging these two. Fine. The other thing is what? 0, 1, 0, 1, 0, 1. And here EB, EB, right? CF. So EB, EB means outputs is same. First thing we have observed. And EB, EB means these two are having same. So again, what can I do? I can remove one of these two, A or C. I am removing C. Wherever C is there, there we need to write now A. So what is that now? Minimize the present state. You can write like this also, not a problem. So if you're not able to understand in one table, removing and all, so you can do this. Present state, next state, and output. Next state for x equal to 0, next state for x equals to 1. Output for x equal 0, output for x equals to 1. So what is it here? A, and here it is E, B, 0, 1. Next, B, what is here? FB, then it is 0, 0. Next, what is here? E, in place of C, what will I write now? What should I write? In place of C, C is removed. In place of C now, A, F, 0, 1. And what about F, B, and here in place of C now, again A, it is a 0, 0. You can observe these two, 0, 0, 0, 0, FB, BA. No possibility for merging. So now again 0, 1, 0, 1, EB, right? 0, 1, 0, 1, EB and AF. Not possible to match. So it is not matching with any of the three cases. So no further minimization is possible. Then what we can say? This is a minimum possible or this is a minimization. How many states are there after minimization? How many states are there after minimization? 4 states. How many states are redundant? 2 states are redundant. 2 states are redundant. Right. 2 states are redundant. Thank you. Thank you, Pallavi. And before that, let me go to the question which I would like to. Try to do this state minimization. State minimization. Classroom practice questions. Very simple. Here itself, you can complete it. These two must be observed. These two must be observed, right? In this, what we can do? First thing is what? Here, 1, 0, 1, 0, EA, CB. Yes, sir. These two can be merged. One can be removed. Let me remove C. Let me remove C. Wherever C is there, what should I write there? D. So if I write D here, if I write B here, then what is that again? AB, 0, 1, 0, 1. One can be removed. So if I remove E, what should I write? D. That's it. Done. No more further reductions because here 0, 0 is there, here 1, 0 is there, here 0, 1 is there. Right? So no possibility for further merging. Removing. So removing two states. How many states are there after minimization? 3 states. Vishnu, please check. Pallavi, you did a mistake. Please check it. 2 states are redundant. 3 states are there after minimization. Let me explain once again. People are having a doubt. Do you have any doubt in this? It is 3 states. So it is absurd. Clear? So if it is clear, nothing is there in this simple question which was given in previous GATE exam. And if you are observing this, what is this here? A simple question. So S naught getting a 0, output is 1. 0, output is 1. From S naught, if you are getting a 1, it is moving to S1 state. 1 by 0. From S1 also again, what is it here? From 1, for 1, output is 0, same state. For 0, it is a. What is it here? If 0 is there, it is getting 1. If it is 1, it is getting 0. What is here? Simple thing. 0 to 1, 1 to 0. Why we have used two different states? S naught is indicating whether we are getting 0 or 1. S naught is getting 0, and S1 is getting 1. Getting logic 0, getting logic 1. The only difference is to differentiate two possibilities. Are we getting 0 or are we getting 1? Yes, Yugashri. Yes, Yugashri. Any problem? Yugashri, you can type if you have any doubt. Yugashri. I think you raised the hand. Do you have any doubt? Yugashri, are you from E or EC? And no need to worry that much if you are from EE. So don't worry about that clearly, because and very rarely, not rarely, once in right 10 or 15 years, once they have asked a question, the two in ESC, university. Yes, I know it is new for you because you are from electrical. I can understand that. So yes. So if you are not able to understand, no need to worry about this FSM for you. For you, university. See, some people are again doubting here. Here, once you are merging, right? What are the first one? These two. If you are merging these two, which one is merged first one? Which one is merged first one? These two. Because AA1010 was there, and here it is CB. As these two are same, these two are same. BC, CB. These two can be merged. Which are those? B and C state can be merged. So I'm removing C. Wherever C is there, there I'm writing B. Because B and C are same, you are confirming. As these two can be merged, B and C, wherever C is there, I'm writing B. Once you are writing B, what we are writing here? AB, and 0101, these two can be merged. Then I'm removing E. Then wherever E is there, I'm writing D. That's it. After that, if you're observing, there is no possibility for further merging. Pallavi and Bhaskar. Pallavi and Bhaskar. Clear? Understood now? Thank you. Thank you. So in this, whatever the input you are applying, it is getting output is complementary. Just when you are verifying this type of functions, what is the functionality of given FSM? Simple thing is apply a serial input data like this 10 10 1101 like this, and apply. From here, what we are getting here input 1, so it is moving to S2 state. Now we are in S2 state. What is the output? 0. What is next input? 0. You are in S1 state, you are getting a 0. When you are getting a 0, what is it here? It is moving to S0 and output is 1. Now we are in S0 state. Now what is the input we are getting? 1. When you are getting 1, it is moving to S1 state. Output is 0. And now we are in S1 state. You are getting input is 1. So for 1, output is 0, same state. Output is 0, same state. Now we are in S1. You are getting a 0 now. So if you are getting a 0, next state is what? S0. Output is 1. Now you are in S0 state. You are getting a 1. Input is 1. Output is 0. It is a S1 state. If you are observing what is it here? Inputs and outputs you are observing exactly one's complement. In such cases, just consider some input sequence and observe what is its functionality. What is its functionality? Right. This is one more question. Read the question first. Yes, Manisha. 1, 0 or zeros or ones we are applying. It is a Here, there is a word ambiguous. What do you mean by ambiguous? Not clear. What do you mean by not clear? Revanta, what happened? Have you typed anything? Right? So what is it here? Ambiguously, not clearly. It is not clearly defined. That is called ambiguity. What do you mean by this? From a state for one input condition, next state is only one. From a state for one input condition, next state is only one. Then it can be designed the system. There is no ambiguity in that. But from a state for one input condition, next states are defined two or more than two. That is called ambiguously defined. See, what we need to understand here is when it is defined, a state diagram, when you are writing a state table, if you are observing from a present state for one input conditions, next state is only one. That can be designed the system. That is called, there is no ambiguity, unambiguous, right? Unambiguous. So if it is defined multiple states for one input condition from a state for one input condition, if you are observing multiple next states, then it is called ambiguously defined. So try to analyze from each and every state, what is the next state, right? So from each and every state, we need to write. How to write? Let us see. Let me write for one state. Let me take a present state, present inputs X, Y, Z, and next state. Let me write for C. For C, what is it here? From C, if you are observing, if Z equal to 0, next state is C. Z equal to 0 means XY can be 0, 0, 0, 1, 1, 0, 1, 1. For all these, next state is C. Anyone having any doubt? From C, if Z equal to 0, XY can be any value. That means XY can be 0, 0, 0, 1, 1, 0, 1, 1. For all these, Z equal to 0, next state is what? C. So from C, X equals to 1, Z equals to 1, what is next state? B. From C, X equals to 1, Z equals to 1, next state is B. So X equals to 1, Z equals to 1. So Y can be 0 or 1. Y can be 0 or 1. X and Z are 1, 1. Y can be 0 or 1. What is the next state? B. Check it correctly. Another condition from C itself, X equals to 1, Y equals to 1. X equals to Y equals to 1. The next state is A. So X equals to 1, Y equals to 1. What about Z? Can be 0, can be 1. What is the next state? It is A. It is A. So if you are observing this definition of a state or system, so 111 condition, 111 condition from C, next state is B. 111 condition, next state is what again? B. Sorry, I might have written one state is less here, right? I forgot to write last one, right? Just a minute. Here it is A, here it is again A. Just a minute. It is A, it is A. And after that, if you are observing, for 111, next state is what? A. For 111, next state is what? B. So, which one is correct? According to the definition, both are correct. But can we design the system? No, it is not possible. Not only this, if you are observing 110 also, it is having ambiguity. So, the state C is not clearly defined, which cannot be designed. So, in state C definition, there is an ambiguity. Yes, Manikanda Chowri. Very good. So, there is an ambiguity. So, what do you mean by ambiguous, sir? It is not clear. clear. That is called ambiguous. That is called ambiguous. So this question, most of you might have done correctly. Check it correctly. Very simple question. So how to observe this? Output Z or output Y is what? These two are logically ANDed. Logically ANDed. So what is it here? Negative edge triggered flip-flops. Two flip-flops inputs are specified. Two flip-flop inputs are specified X1, X2. So these two flip-flops are responding to X1, X2 at negative edges of clock. And two flip-flops outputs are ANDed. Very simple. So at negative edges of clock, first let me find negative edges of clock. There, what we have input 0, 0, and here it is 1, 0, and 1, 0, then 1, 1. So what we get here 0, 0, 1, 0, sorry, 0, 0, 1, 0, and again 1, 0, again 1, 1. So what is it here? Initially assume it was 0. At this negative edge, what is it here? When you are observing AND gate output, 0, 0, AND gate output is 0. Again 1, 0, AND gate output is 0. Again 1, 0, AND gate output is 0. At this negative edge, as both are becoming 1, 1, output is becoming 1. Output Y. So option is W3. So answer is C. Very simple question. After understanding edge triggered flip-flop, which was previously given gate exam question. Gate exam question. Very simple question. And coming to this. So 0, 1, 0, 2, 0, 3. Before discussing this, let me discuss one more question. What is it here? For example, if it is 0 to 0, 1 to 1, then 2 to 2, and 3 to 3, again back to 0. Just let me discuss this, then I'll talk to that question later. Right. So 0 to 0, then 0 to 1, 1 to 1, 2 to 2, 2 to 3, 3 to 3, again 3 to 0. How many flip-flops required to design this counter? This counter. Now, what is it here? Here, if I say that 0 and 1, 2, 3, only 4 possibilities. 0, 1, 2, 3. So 0 can be represented with 0, 0, 1 can be represented with 0, 1, 2 can be represented with 1, 0, 3 can be represented with 1, 1. So let me write a present state and next state to design the system. So 0, 0 to 0, 0, right? 0, 0 to 0, 1, 0, 1 to, what is the next one? Again 0, 1, 0, 1 to again 1, 0, right? From 1, 0 again, what is that? 1, 0. From 1, 0 now, 1, 1. From 1, 1, what is the next one? 1, 1. And from 1, 1 again, 0, 0. Anyone has any doubt how I'm writing this? Simply from the given. I'm not discussing this question, I'm discussing a new question. Now, what can we do? You can design the system, but there is a problem here. Ambiguity is there. What is the ambiguity? 0, 0 next state is 0, 0, 0, 0 next state is 0, 1. That means these two are not same because these two are having two different next states. It looks like 0, 0 is one state, but these two 0, 0 is not same because once it is giving 0, 0 next state and second time it is giving 0, 1 next state. Again 0, 1 is not same here because once it is giving 0, 1, once it is giving 1, 0. Next one is what? 1, 0 to 1, 0, 1, 0 to 1, 1, 1, 1 to 1, 1, 1, 1 to 0, 0. That means these two 0, 0s are not same. These two 0, 1s are not same. These two 1, 0s are not same. These two 1, 1s are not same. So these two are not same. That you know, but system doesn't know. To differentiate by system, I need to add extra bit. So to differentiate these two possibilities, I'm saying that 0, 1. Let me take one more bit Q2. Again, these two are not same. Let me add 0, 1. Again, these two are not same. 0, 1. Again, these two are not same. 0, 1. Because I need to differentiate two possibilities. One bit is sufficient. If I have three possibilities, I have to differentiate three possibilities. Then what should I do? Adding 2 bits extra. I have to differentiate 4 possibilities, 2 bit extra. And if I want to differentiate 5 possibilities, I need 3 bits. 5 to 8, 3 bits. 8 and above up to 16, it is 4 bits and so and so. You can understand it here. Here, I'm using 1 bit extra because here we have only 2 possibilities should be differentiated. Then what about next state? Again, you need to write it because it must be matching, right? 1, 0, 1, 0, 1, 0, 1, 0. By designing system, read only on Q1, Q0. Read only on Q1, Q0. For designing, one flip-flop is extra, but reading is only on Q1, Q0, two flip-flops. So one flip-flop is extra. The reason is there is an ambiguity in the state definition. State definition, there is ambiguity. That is the reason that ambiguity should be eliminated. How can I eliminate? These two are not same that you are understanding to understand by system by adding extra bit. As it is only two possibilities, one bit was sufficient. One bit was sufficient. And coming to this one, what is it here? 0, 1, 0, 2, 0, 3. Not required to design. Not required to design. Simple thing. I need to say how many flip-flops. So now, what is it here? Q1, Q0. Again say Q1, Q0. Then what is it here? 0, 0 to 0, 1, 0, 1 to 0, 0. I'm writing 0 is 0, 0, 1 is 0, 1, 2 is 1, 0, 3 is 1, 1. I'm writing wrongly, right? Just a minute. Right. This is what we have, right? Now I'm writing that 0, 1 to again 0, 0. And from 0, 0, what is it? 1, 0. From 1, 0 again 0, 0. From 0, 0 again 1, 1. From 1, 1 again 0, 0. This is what we have. But again, we are observing there is ambiguity. What is it? 0, 0 is having 0, 1. 0, 0 having 1, 0. 0, 0 having 1, 1. How many times 0, 0 is there? 3 times. Are they same? No, they are not same. When they are not same, we have to differentiate. To differentiate three possibilities, how many bits extra? 2 bits. Already we are using 2 flip-flops. Then, and 2 more bits extra required. 2 more bits extra required. Then, how many flip-flops total? How many flip-flops total? To differentiate 0, 0s, 3 times is there. For 3 times, you need 2 bits extra. So, 2 plus 2, it is becoming 4 flip-flops. Neeraj Meshram. Right. From each and every present state, if next states are defined multiple, cannot be designed. Neeraj Meshram. Same as ambiguity, what we have discussed just now. There should not be ambiguity. Then only we can design the system. From a state, if next states are multiple, how can I design? How can I specify that? It is not possible. So, from a state, if you are having multiple next states, you need to confirm, right? These are same or not. If these are not same, yes, these are different conditions that you know, but counter does not know, system does not know. That is the reason I need to say that those are not same. Those are not same means I need to differentiate by adding extra bits only, that you are understanding. This is a right 0, 0 first time, 0, 0 second time, 0, 0 third time. That you have a counter in your mind, first time, second time, third time. But how system can define? How system can understand? By adding extra bits only. As it is 3 times, it is to be differentiated. Or 3 possibilities should be differentiated. So for 3 possibilities, 2 bit extra, 4 possibilities, 2 bit extra, and 5 possibilities, 3 bits extra, and 6 possibilities, and so on. So up to 8, it is 3 bits only, and 9 and above up to 16, it is 4 bits extra. So how many possibilities are there? Depending on that, we need to design the system. For example, if I say like this. Here only, a sequence I write here. 0, 1, 2, 2, 3, 3, 3, 4, 4, 4, so and so, 15, 15, right? You can guess how many times it can be. 15. If this is sequence, how many flip-flops required? Please guess. How many flip-flops required to design the system? How many flip-flops required to design the system? Excellent. Excellent. Some are saying correctly. Yes. Yes, you are right. First of all, to say 0 to 15, 0 to 15, how many bits? 4 bits, right? 0, 0, 0 to 1, 1, 1, 1. But this 15 is existing for how many times? 15 times. To differentiate these 15 possibilities, we need again 4 bits extra. 4 plus 4, 8. Excellent question, right? Sorry. Just a minute. So to differentiate 0 to 15, to differentiate 0 to 15, we have just a minute. Let me open that. What was the slide number? Right. Here, first to write 0 to 15, we need 4 bits. And 15 is existing for 15 times means we need 4 bits extra. So to differentiate maximum possibilities in this 15. 15 times it must be differentiated. Then 4 bits extra. Then what is it here? 4 plus 4, 8 bits required. Very good. Excellent. So it is not only one question. We can frame any such questions. Please understand correctly. So coming to this question. Check it correctly. What is it? It is happening. If you are understanding what I discussed, go through this. Yes. Right. Here problem is some extra inputs is given. N bit, it is mod n counter using a synchronous counter. It's not asynchronous counter, a synchronous counter by synchronous binary up counter with synchronous clear input. With the synchronous clear input is shown in figure. The value of n is very simple thing. So let me analyze with respect to clock. With respect to clock, please focus on this. What is happening, you can understand. Right. So let me say it is a clock. It is a clock. Before occurrence of the clock, if it is 0, 0, 0, 0. After clock edge occurrence 0, 0, 0, 1. After this 0, 0, 1, 0. And for this, what is it here? Clear pin was logic 1. For all these, what is it here? Clear pin was logic 1. Clear pin was logic 1. Now let me write the states. Here it is 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0. Am I right? 0, 1, 1, 0. So till 0, 1, 1, 0, NAND gate output will be logic 1 only. Once QB, QC are both are becoming 1, 1, NAND gate output is becoming 0. NAND gate output is becoming 0. Correct? Yes or no? After this clock edge occurrence, we can see 0, 1, 1, 0. Once it is getting 0, 1, 1, 0, clear is going to 0. Clear is going to 0 means here it is 0 means it is enabling. Clear is enabled. but clear operation will be performed at next clock edge occurrence. Next clock edge occurrence. Am I right? Anyone has any questions? Because it is synchronous clear. Is it possible to have synchronous clear? Yes, we can have synchronous clear input. Why? It is a synchronous counter. This is clock for all the flip-flop. Yes, I can provide clock for all the flip-flop at common point of time. Right? If I provide clock for all the flip-flop at common point of time, yes, obviously, I can clear all the flip-flop at this common point of time. As it is possible to provide clock for all the flip-flop at common point of time. Yes, at the common point of time, I can clear all the flip-flops. But in asynchronous counter, it was not possible because it is not possible to provide clock for all the flip-flops. Then what you are observing? What you are observing? Last state 0110 is not temporary here. In asynchronous counter, it was becoming temporary, but here 0110 is available for one clock cycle. Then 0110 also counted. Then modulus of counter is from 0000 to 0110. If you are counting, it is total 7 states. It is 7 states. The effect of synchronous counter. See, if you are understanding concept, it is easy to apply. In asynchronous counter, there was a problem. We were not able to provide the clock for all the flip-flops. That is the reason we were going with asynchronous clear inputs. I want to clear all the flip-flop at common point of time. At that common point of time, providing clock edge for all the flip-flops was not possible. That is the reason it was preferable asynchronous clear input to clear all the flip-flops in asynchronous counter. But in synchronous counters, yes, we are providing clock edge for all the flip-flop at common point of time. That means it is possible to clear all the flip-flops at common point of time, even though we are using synchronous clear inputs. Even though we are using synchronous clear inputs. Right? That's what clearly I explained. How it will be asynchronous clear, how it will be synchronous clear, and how we are confirming that it is required to use asynchronous clear in asynchronous counter whenever you want to clear or preset at common point of time all the flip-flops that I clearly explained. If you right, yes, in the same counter, instead of synchronous clear, it is asynchronous clear. So don't think that in synchronous counter it must be synchronous clear inputs. Asynchronous counter must be having asynchronous clear input. No, I did not say. In this same counter, if all the flip-flops are having asynchronous clear inputs, then it would have been again mod 6, same as asynchronous. In this same synchronous counter, if the flip-flops are having asynchronous clear inputs, once again, modulus of counter is 6 only. Modulus of counter is 6 only. Right? So that's the way we need to answer the questions. We need to answer the questions. Yeah, in this, even though you are not defining which one is MSB, which one is LSB, doesn't matter. In this, it is not required to specify. Whichever the order you are considering, it will be same sequence because middle one QB, QC, both are expected 1-1. You wish you can use any order in this question. But if you are using any specific sequence on clearings, then obviously they have to specify. They have to specify. Chakrabarti, good question. In this, what is the order doesn't matter for us. Right? That's what I'm saying, Chakrabarti. If I'm using any other state to clear, they have to specify. They have to specify. Listen carefully. Yes. If it is used any other state to clear, they have to specify which one is MSB, which one is LSB. Which one is MSB, which one is LSB, they have to specify. Otherwise, at least they have to use notation Q3, Q2, Q1, Q0. The numbering is confirming that which one is MSB, which one is LSB. Which one is LSB. Yeah, this is a very simple question in asynchronous counter as we discussed earlier. Right? In asynchronous counter as we discussed earlier, if this is a clock, for example, if this is a clock, then what we discussed, First flip-flop output is delayed by at a positive edge of clock. It is delayed by delta, which is flip-flop delay. Q naught, it is delayed by delta. Everywhere it is delayed by delta. This is Q1. What about Q1? Again, complementing at every positive edge. Q1 again delta, it is delayed. This is delta, this is delta, this duration is what? If I say T1, it is T1 plus 2 delta. How much is this cycle duration? 40, right? This 40. T1 plus 2 delta and 40. That is the correct answer. Option is T1 plus 2 delta and 40. Which is already analyzed, not a new question. Which we have already discussed. Which we have already discussed. Right? This is also discussed already. This is also I discussed. Right? This is what I was saying, electrical gate question. It was given in POS. Which one can be the correct? As we know that T to JK, we have done this conversion, same example. So T is equals to what is it here? J Q bar plus KQ. Or what is the other one? J plus Q plus and K plus Q bar. J plus Q and K plus Q bar. Which option is correct now? Option is right. It is not new one. Already I have discussed in the class. J plus Q. Sorry, it is wrong, right? It is wrong. J plus Q. Where is it? This one. J plus Q and K plus Q bar. Right? JQ bar plus KQ. JQ bar plus KQ or J plus Q and K plus Q bar. It is implemented in POS. Right? This was a question 2014 gate electrical. Simple question. Observe this, sir. What is the question and how to answer this question? Try to analyze this question. Read the question. The first thing we must know is, right, when you are applying a voltage waveform across a resistor, let me say it is 0 volts, it is a voltage V. Voltage V. What is the average power? This is a voltage waveform across the resistor. Then what is it here? If it is a T on, if it is T, what is here? 1 by T integral 0 to T P of T dt, power, average power. Is it correct? Average formula? 1 by T integral 0 to T F of T dt. Then 1 by T integral 0 to T on, 0 to T on, what is that here? V square by R into dt plus plus what is the next one? Are you there? Integral t on to t 0 dt. Right? So this is 0, then 1 by t, v square by r is constant, v square by r, integral 0 to t on 1 dt. What is that here? V square by r into 1 by t, integral t. Integral 1 is what? T, 0 to t on. This is a formula we need to know. V square by r, if I substitute t on minus 0, what is it here? T on by t. What is it here? V square by r is power. V square by r is power. Then what is it here? T on by t. T on by t. So what is T on by t? Duty cycle of output waveform. Duty cycle of output waveform. Check it correctly. Very simple. V square by r, T on by t. So what is the waveform we are applying across the resistor? In that V is voltage, R is resistance. If I say that V square by R is power, average power we can calculate 1 by t integral 0 to t, f of t dt. F is what? Power of t. So 1 by t integral 0 to t on, what is the voltage we have? V. So V square by R dt. Plus the integral t on to t, it is the power is 0 because V is 0. Now, if I expand this, finally what we are getting here? V square by R into t on by t. Very simple question. V square by R into t on by t. That's it. So now, what is that duty cycle? So don't consider duty cycle of clock because clock is not applied across the resistor. Check it correctly. Clock is not applied across the resistor. Unnecessarily, it is given extra information, 30% duty cycle of the clock. It is not required to consider because what is the duty cycle of the waveform we are considering? What is it on time compared to off time? So let us see what is it here. So what is the waveform we get across the resistor? For that, what should I use here? If I say Q1, right? Q1, Q2, Q3, Q4, Q5 is initially loaded with 0, 1, 0, 1, 0. Am I right? 0, 1, 0, 1, 0. Then what is the next state of this? What is the next state of this? Is this which counter is this? Ring counter, 5-bit ring counter. Check it. It is 5-bit ring counter. What is applied here? As D input, output of last flip flop. It is a register, 5-bit register. Output of last flip flop is applied as input to the first flip flop. Let me say what is the next state? So 0 is becoming Q1 and remaining are shifted 0, 1, 0, 1. And what about next state? 1, 0, 0, 1, 0. Am I right? This one is becoming here. These are shifted right. Again 0, 1, 0, 0, 1. Again, what is that? 1, 0, 1, 0, 0. Again, initial 0, 1, 0, 1, 0. So again, back to initial means I can say it is back to this initial. Instead of writing again state, what we can say it is going back. What is across resistor? Q3 logical or Q5? Q3 logical or with Q5. That is across resistor. Let me say what is that Y waveform. Logically or 0, here it is 1, here it is 0, here it is 1, here it is 1, here it is 0 again. Then again back to this. So what is duty cycle of this waveform? Can you say? No. The last one should not be considered, right? Last one should not be considered. Sorry. Right. What is duty cycle of this waveform? Can you say? What is duty cycle of this? Are you there? So each state is a one clock cycle. Each state is one clock cycle. What will be on time? 3 clock cycle. What is off time? 2 clock cycles. If I calculate this average power, V square is how much? 5 volts is given. 5 square divided by R is how much? 10K. What is the T on? 3 clock cycle. What is cycle duration total? 5 clock cycle. Check it correctly. It is 60% duty cycle. It is 60% duty cycle. Check it correctly. So each state is existing for 1 clock cycle because it is synchronous. Each state is existing for 1 clock cycle. So how many clock cycles is logic 1? 3 clock cycle. How many clock cycles total? 5 clock cycles. So on time is how much? 3 clock cycles. Total cycle duration is how much? 5 clock cycles. So how much we get here? 1.5 milliwatts. Calculate. T gets cancelled. T gets cancelled. And substitute and calculate the value. It becomes 1.5 milliwatts. So K is there. Forget about that. So 5 square is 25. 25 by 5 is how much? 25 by 5 is 5. 5 3 is 15. 15 by 10, it is 1.5. Kilo is becoming milli. That's it. 5 square equals 25. 25 by 5 is 5. 5 3 is 15. 15 by 10 is 1.5. 1.5 divided by K is 1.5 milli. 1.5 milliwatts. So they have given extra information to bluff you. If duty cycle, if you are considering 30%, we are getting how much value? Instead of 60%, if it is 30%, it becomes how much? 0.75 milliwatts. Someone has given that answer also by using duty cycle. Right? 0.75. Kumar, that is wrong. So it is not applied clock across the resistor. It is applied flip-flop outputs. Flip-flop outputs. As inputs of OR gate output is connected. Yes, Bhaskar. T on divided by total cycle duration. Right? Vamshi Krishna. Wait. T on divided by what is cycle duration? T on by T. T on by T. T on by T. Already we have discussed these questions, sir. Some simple questions are there. This is what we have discussed about FSM, which is required for our exams. So be clear about this. Next, we start with the CMOS logic families. CMOS logic families. What is CMOS? Complementary MOS. So in which we have N-channel MOSFETs as well as P-channel MOSFETs. So N-channel MOSFET as well as P-channel MOSFETs. Annapurni, required a break? Okay, let us take a small break for 15 minutes. We'll continue after the break. So I'll be back exactly at 9 a.m. Yes. I'm back. If anyone is there from electrical, they can leave. If you are staying there, I don't have any problem. If you want to learn anything new, or if you want to learn, not a problem. It's for EC and IN. No, Pratik. It's not for E. Yes, Abhijit. Yes. Harsha, I did not understand what is that. Yes, Mangesh, it is done. Revant, it is done. It is done for E. It is completed. Prashant, it is completed. If you are interested, you can stay back, not a problem. Yeah, it may be. It will be scheduled, Abhijit. Please wait. And stay tuned. It will be updated. Abhijit. Yes, we'll interact once again if required. And so I'll be there to help you. Yes, Manikanta, I'll talk to you. Not a problem. You can call me at any time. I'll talk to you. Don't worry. I'm there to help you. You have my number as well as email ID also. So we'll talk about that later. Manikanta. Right. Yeah, it is there, Naresh Kumar. That will be done later. Naresh Kumar, it is there. That I'll do later for ESC. This here I'm discussing only digital part. Okay. If you are from electrical, if you are leaving the session, all the best. Right? Be in touch to get more inputs. All the best once again. Not there. Venkana is not there. It's not for you. Venkana. Right. Okay. Then CMOS, complementary metal oxide semiconductor. Complementary metal oxide semiconductor. So in this, we are going to use both N-channel MOSFETs as well as P-channel MOSFETs. Both N-channel MOSFETs as well as P-channel MOSFETs. Arsha, please wait. Uh, I will talk to you later. Please wait, Arsha. It is not there, Jaswant. If you want to attend, I don't have any problem. Jaswant, stay back for some more time if you're interested, right? Please let me go with this. Complementary metal oxide semiconductor, CMOS, in which in which we have both N-channel MOSFET as well as P-channel MOSFETs. And we are using P-channel MOSFETs in upper circuit and N-channel MOSFET in down circuit, or we say separately pull-up network and pull-down network. What is this pull-up network and pull-down network? Before understanding that, let us understand simple operation of N-channel MOSFET and P-channel MOSFET. N-channel MOSFET and P-channel MOSFET. The representation of N-channel MOSFET is this, right? So in which we have a gate terminal, drain terminal, and source terminal. Source terminal. So these drain and source are interchangeable. This drain and source are interchangeable. Which one is drain, which one is source is not possible to define with respect to terminals, which is after manufacturing. If isolated MOSFET is there, there also we cannot say which one is drain, which one is source. But how can we differentiate drain and source in analyzing is so whichever the terminal is getting higher potential is drain, lower potential is source. Comparatively, in N-channel MOSFET, whichever the terminal is getting higher potential is a drain and the other is a source for N-channel MOSFET. And similarly for P-channel MOSFET, while writing itself, upper one we say S, lower one we say drain, it is gate. So whichever the terminal is getting higher potential is a source and the other is a drain. The other is drain. This is what we need to understand. So while writing also, if you are observing, while writing P-channel MOSFET, we are writing upper one is source, lower one is drain. Because assuming that supply is there in the upper, so whichever is near to the supply is source, whichever is far away from supply is drain for a P-channel MOSFET. For N-channel MOSFET, whichever is near to the supply is drain, whichever is far away from supply is a source. That's what another way of convention to understand which one is drain, which one is source. Which one is drain, which one is source, we can understand what is it here. In N-channel MOSFET, higher potential is drain, lower potential is source. And for P-channel MOSFET, higher potential is source, lower potential is drain. That's what we need to understand. Right. So one more thing we need to understand, when it can be on, when it can be off. These conditions also important. These conditions also important. What is it here? Let us see. For N-channel MOSFET, if this is drain, which is a source, here it is gate. What is the voltage required to switch on this N-channel MOSFET? VGS, gate to source potential, must be greater than or equals to threshold voltage of N-channel MOSFET. Then it is on, right? Else it is off. So VGS less than VTN, it must be off. Before that, VGS must be positive. VGS must be positive and VGS greater than or equals to VTN. Then it is on. If VGS is less than VTN, it can be negative or it can be any value less than VTN. That is condition is off. Listen carefully. VGS must be positive to create the channel. To create the channel between drain and source. To start conduction between drain and source. So induced channel in MOSFET. In MOSFET, it is induced channel. Enhancement MOSFET, which is induced channel in which gate potential is inducing the channel. Then, if you are applying voltage difference between drain and source, there will be conduction. There will be conduction. There will be conduction in the channel. Now, for P-channel MOSFET, it is source, it is a drain. Here it is gate. What is it here? VGS must be negative and VGS must be less than VTP, less than or equals to VTP. Understand correctly? VTP. Already VTP is negative. VTP is negative. For these two conditions, it is going to be on, and if VGS greater than VTP, then it is off. It is off. So one more thing here, VTN is a positive, VTP is a negative. That's what we need to understand. Threshold voltage of N-channel MOSFET is positive. Threshold voltage of P-channel MOSFET is negative. Between gate and source terminal, we are applying the potential. That potential, if it is positive, more positive than VTN, then it is on. And VGS is negative. VGS is negative and is more negative than VTP. Then P-channel MOSFET is on. So some of you might have gone through these devices already. But some people may be new to this concepts, new to the coachings. For that is the reason I've been discussing all these points to understand concept. But in reality, all these points you are going to study in devices once again. But I wanted to give you clarity about this in my discussions also. So whichever is required for digital point of view, I'm covering. I'm not covering devices. I'm not covering VLSI. So you are going to study in depth of this again after some more time in device or VLSI. So at this moment, whichever is required for our CMOS logic family, I am covering. So I'm not discussing how channel will be created. So the points which are required for analyzing CMOS logic gates, I am explaining. Right now, anyone has any doubts in this? May not be Annapurni. I will try my level best. Right. If possible to complete today, I will do. Otherwise, there may be one session 7 to 9 only for EC. 7 to 9 may be there. Right. VTN is positive, VTP is negative. VTN positive, VTP is negative. VTP is negative. Yes, enhancement only we use for getting better control. Venkat Brahma Reddy. We don't have that much control on depletion MOSFET. We don't have that much control on depletion MOSFET. Venkana we see later. Not in this schedule, sir. It is not planned. Right. We'll do later. Venkana. Not now. Right. Right. So to use depletion MOSFET, depletion MOSFET is not having that much control, as we know already. If you have studied the devices already, so depletion MOSFET is not having that much control because it is already pre-existing. Because the control signal is not that much having control. Which one is control signal here? Gate terminal potential is controlling whether switch is on or off. But depletion MOSFET is a pre-designed or pre-existing channel. Without gate voltage itself, it is conducting between drain and source. That we don't accept as a switch. As a switch, we want to have a full control on and off. So without applying gate potential also, if you are applying voltage difference between drain and source also, it is conducting in depletion MOSFET. That means we don't have control on switch. That is not accepted. That is not accepted. Venkat Brahma Reddy. Venkata Brahma Reddy, right? Understood? So depletion MOSFET is not having that much control. That is the reason in our digital IC, we never use depletion MOSFET. We prefer to use enhancement MOSFET only. Enhancement MOSFET is having a better control, whether conducting or not conducting. Switch is on or switch is off, is having better control, right? That is the reason we prefer to use enhancement MOSFET only, right? So as we are discussing digital point of view, we have only two different voltages, logic 1 and logic 0. We don't have that intermediate voltages that we do in analog as well as EDC. What is it here? All the voltage variations we think, but here we are interested in analyzing only two different voltages, logic 1 and logic 0. If I say logic 1 is VDD, logic 0 is 0 volts ground. Logic 1 is a VDD. Logic 0 is ground, which is 0 volts. For example, in my design, if I'm going with the VDD 5 volts, VSS, which is 0 volts ground, right? This is a, don't say it is a VSS or a Yovish. What we can say, ground. So it is a logic 1, it is a logic 1, it is a logic 0. It is logic 0. See, VSS is not source voltage, it is VSS which is ground. So it is 0 volts we are using. Logic 0 is 0 volts, logic 1 is 5 volts for understanding concept only. Nowadays we are using logic 1 is lesser than 1 volt in the recent technologies. And recently it is fabricated. IBM fabricated a 2 nanometer IC also. 2 nanometer IC also already manufactured. So where we are, just think. In the 2 nanometer, it is less than 0.5 volts is logic 1. Less than 0.5 volts is a logic 1. We are studying about a logic 1 with 5 volts to understand the concept. So it is not 5 volts always, right? Ashish, it is not required. It is not required, right? So here we have a, what is it here? If you are interested, I will take to waste your time. Not a problem, right? Gate, drain, and source. So here source is at lower potential. What can we apply at gate terminal? Logic 1 or logic 0 to switch on N-channel MOSFET. To switch on N-channel MOSFET, what should I apply at gate terminal? Logic 1 or logic? When we have only two different voltages, what should be connected at gate terminal? Logic 1 only, right? Logic 1 only, because gate to source potential must be positive. Gate to source potential must be positive. Gate to source potential is a positive. Then only it can switch on. Then only it can switch on. Once again, what is it here? Gate to source potential must be positive to switch on. To switch on. So we need to connect the gate at a positive potential only. Gate at a positive potential only. Then what we can say here, gate to source potential must be positive, means gate must be higher potential than source. The possibility here, it can be a logic 1. So here we have only two possibilities. One is logic 1, other one is logic 2. Then what should be connected to gate? A logic 1 only. A logic 1 only. So when I apply gate is at logic 1, or if gate terminal is getting logic 1 for N-channel MOSFET, we can consider switch is on. NMOS switch is on when gate is connected to logic 1. When gate is connected to logic 1, let me say that, yes, that you will understand in a device. Please hold on. So when we are applying that gate to source potential positive, then only it can switch on. Then only it can switch on. So if you are observing that drain is at higher potential, source is at lower potential, gate to source potential must be positive. For that, gate is connected to a logic 1 to switch on this N-channel MOSFET. So in N-channel MOSFET, if the gate is getting a logic 1 potential, it can be switched on. If gate is getting logic 0, it is off. So when it is getting logic 0, the source may be getting any other voltages. So it can be 0, it can be above that, depending on construction, sir. Depending on construction. So if gate is at logic 0, it cannot be a positive potential gate to source, sir. So if VTN, for example, VTN is 1 volt, VTP is minus 1 volt. Let me consider to understand the concept. VTN, threshold voltage of N-channel MOSFET is plus 1 volt. Threshold voltage of P-channel MOSFET is minus 1 volt. That means gate to source potential must be more positive. It is more than plus 1 volt. Then it can switch on. For that, here you need to apply logic 1, which we say logic 1 is what? VDD. So we can say it is plus 5 volts. It is plus 5 volts. We are applying a logic 1, which is VDD, which is plus 5 volts in my discussion. Then it can be switched on. Now, what about P-channel MOSFET? This is gate, this is source, this is drain. And Brahma ready. For your doubt, in N-channel MOSFET, current is flowing from drain to source internally. This is the current direction because it is higher potential with lower potential. Always current is flowing from higher potential, lower potential. And here it is flowing from source to drain. That you will understand later after getting into devices. Please let me go with the required concepts. Required concepts. See what we have here. Source to drain. We have a current flow. But what must be the source here? What is the source here? Higher potential compared to drain. So to switch on this P-channel MOSFET, what should I connect here at gate terminal? Lower potential. Because source is at higher potential, gate to source potential must be negative. For that, I need to connect here a logic 0, which is 0 volts. Which is 0 volts. So to switch on P-channel MOSFET, source is at higher potential, gate is at lower potential, gate is at logic 0, then it is lower potential. So if it is getting the voltage greater than 0 volts, obviously it can switch on. It can switch on. So gate to source potential is negative, then it can switch on. To make it negative, gate must be connected to a lowest potential, which is logic 0 in my design is 0 volts. Is 0 volts. Who said Brahma Reddy? If you are assuming it will not be working as that. Who said it must be drain to source only? If someone has said that, it is a wrong concept. I am saying that with a little bit experience what I have in industry as well as teaching from textbooks which I have read, I am confirming that Brahma Reddy. It is not always drain to source. It is drain to source only in N-channel MOSFET. If it is P-channel MOSFET, it is flowing source to drain internally. Even though you are mentioning it as ID, right? Even though you are, it is mentioned ID, it is from source to drain internally. When you are applying that source is at higher potential, where is the possibility for getting current from drain to source? Check it correctly. When you are connecting source is at higher potential than drain, because when you are applying that positive potential, it must be sourcing holes, because P-channel MOSFET is expecting holes must be injected into the channel. There I need to connect a positive potential. Sourcing the carriers is source terminal. For P-channel MOSFET, sourcing is a positive potential because it has to repel the holes into the channel. Their channel is getting P-type carriers, which are holes. And here it must be right, sourcing. Which one is sourcing here? Electrons, negative terminal, right? So draining, when you are applying a positive potential here, when you are applying positive potential at drain, it is draining the electrons. N-channel MOSFET, where it is draining the electrons. Please understand. Don't make me to give you device basics now, please. See what is happening here. When you are applying a positive potential, higher potential here, it is draining electrons because positive potential is attracting electron from the channel. So the electrons are leaving the channel is a drain terminal. So here, when you are applying positive potential, it is sourcing P-type carriers because positive potential is repelling the holes. That means it is providing the holes into the channel. That is sourcing. So here, if I am applying positive potential here, positive potential is attracting the electrons. So it is attracting the electrons means it is out of this channel, that is draining, and other terminal will be source. Here, when I am applying positive potential, higher potential is positive potential if I say, so there it is sourcing the holes. Brahma Reddy. Is that clear now? Yes. So N type or P types is also important. Now finally, what is it here? From this conclusion, what is it here? If gate is connected to logic 1 potential, logic 1, N-channel MOSFET is on. When gate is connected to logic 0, P-channel MOSFET is on. Once again, N-channel MOSFET is on when gate is connected to logic 1. P-channel MOSFET is on when gate is connected to logic 0. Logic 0. Once again, logic 1 is switching on N-channel MOSFET. Logic 0 is switching on P-channel MOSFET. To make it gate to source potential negative, I need to apply gate lower potential than source. Then the possibility is a logic 0 only. Logic 0 only. So when we are coming to CMOS, what we see here, we have two types of networks. One is a pull-up network, other one is pull-down network. If I say VDD, it is ground VSS. If I say I0, I1 and I n minus 1, n bits. This is what a block diagram of CMOS. One is having pull-up network, other one is pull-down network. So pull-up network is nothing but output node is pulled to logic 1. So when pull-up network is on, output is pulled to logic 1, which is VDD. And when pull-down network is on, output is pulled to logic 0. So that means what we are expecting here, at given instant of time, only one network should be on. Only one network should be on. Try to understand correctly. Only one network should be on at given instant of time, because this must be pulled to high or this must be pulled to low. So pull-up network is pulling that output to logic 1 potential when this network is on, and pull-down network is on, then output is pulled to logic 0. Output is pulled to logic 0. Pull-up and pull-down network. And these two must be mutually exclusive. What do you mean mutually exclusive? If one is conducting, other one should not be conducting. If one is on, other one should not be on. That means these two are mutually exclusive. Then what we can say here, the capacitance may be charging. After charging is done, there won't be any charge exchange, because when this network is on, VDD and CL is charged to expected. That is VDD. Then after charging to VDD, there won't be charge exchange. There won't be power dissipation. Even though it is discharging, this will be off. There will be disconnection from VDD for output Y. So there is disconnection. Then when this only on, the charge in this capacitor will be dissipated. That is a grounding. So whatever the energy is there in the capacitor will be dissipated. After dissipation is done, no more power consumption. That means when you are constructing these two networks are mutually exclusive, we can eliminate static power. What is static power? When inputs are stable. When inputs are stable, so what we can say is stable condition, only one network is on means, so in pull-up network, if pull-up network is on, once capacitor is charged to VDD, no further charge exchange, there won't be any power dissipation. Because I'm applying a stable inputs that are giving conditions, only pull-up network is on. Then what happens here? This output is charged to VDD. Further charge exchange will be there. Further current drawn from supply will not be there. Then further power consumption will not be. Once it is charged, charging is done. For charging, it is consuming power. But after charging is done, there won't be any charge exchange. So except leakage current. Except a very small leakage current. So in MOSFET, that is also minimized. That is also minimized. So what we can say here, in CMOS, as there is no possibility for switching on this both N-channel MOSFET and P-channel MOSFETs or pull-up network and pull-down network in static input conditions. In static input conditions, there won't be possibility for switching on both pull-up and pull-down network. That is the reason. That is the reason what we can say. There won't be static power. But while chargings and dischargings, the energy consumed or the power is dissipated. That is called dynamic power. When inputs and outputs are switching, there will be power consumption. That dissipation of power is called dynamic power. When inputs are stable and outputs are stable, there won't be path from supply to ground. There won't be power consumption. That is called static power is eliminated in CMOS. The conditions is here pull-up network and pull-down network are constructed mutually exclusive. At given instant of time, only one is conducting, other one is not conducting. How can we construct this mutually exclusive pull-up and pull-down networks? Is very simple. Pull-up and pull-down networks are dual in nature. point should be understood correctly. Pull up and pull down networks are dual in nature, and those pull up and pull down networks are constructed using complementary MOSFETs. If one is on, the other network, same transistor will be off. What is here? Complementary MOSFETs we are using. In one, we are using N-channel MOSFET, other one we are using P-channel MOSFET. So two networks are dual in nature, and switch on and off conditions is complementary. Once again, try to understand points correctly. I'm going to apply very basic point here. These two networks are dual in nature, and also these two networks are constructed using switches which are complementary. So dual, then complementing switch. What is it, sir? What is that? De Morgan's law. To get a complementary function. Do you remember? After writing dual, complementing each literal is giving complement of a function. Then what we can say, construction itself, while constructing using switches, so you are using dual nature in constructing. What do you mean by this? Switches in series are replaced with parallel, and switches in parallel is replaced with the series. So dual in nature in construction, and on and off conditions is complementary, because we are using two complementary MOSFETs. What is it here? One is N-channel MOSFET, other one is P-channel MOSFET. If one is on, the other one will be off when you are applying same input. Same input when you are applying, obviously one is on, other will be off. That means these two are complementary switches. After taking dual, complementing each literal is giving complement of a function. That means how we are making that these two networks are mutually exclusive. This is the concept. In CMOS, what we are doing, switches are constructed in dual in nature and constructed using complementary MOSFETs. So dual complementing each switch is complementary switch or complementary function. Then when one is on, other one should be off. Yes, we are achieving expected to eliminate static power. Eliminate static power. So finally, what is it here? We are constructing using complementary MOSFETs, and that too dual network. Then obviously these two functions will be complementary in nature. That means only one will be on for stable input condition. If one is on, other one will be off, and vice versa, and vice versa. For given stable inputs, only one network will be on. Only one network will be on. Anyone has any questions in this? No, Annapurni, don't analyze in that way. Right? Only one is on at given instant of time. Any questions in understanding how these two will be mutually exclusive? How these two will be mutually exclusive? Any doubts in that? All those will be right in analog point of view. In analog point of view. It is not like that, Dinesh Sai. The way you are understanding is different. When inputs are stable, so whatever the power dissipation is called static power. When inputs are switching, outputs are also switching. When outputs is switching, there is a consumption of power, because already it was at logic, assume that it was at logic 0. When inputs are applied, which are switching on this pull-up network, then this capacitor has charged to VDD. That means it is drawing current. And when once again, when you are applying input condition, which are switching from logic 1 to logic 0, the energy stored in this capacitor is dissipated through pull-down network. That is called dynamic power. When inputs are switching, outputs are switching. Then output is charging and discharging. From where it is charging? From supply only it is charging. And the energy stored in this capacitor, again when it is switching from logic 1 to logic 0, the energy stored in the capacitor is dissipated. That is called switching power or dynamic power, which includes two more. Dynamic power is included into two parts, is considered into two parts. One is a short circuit power, other one is switching power. Short circuit power you are going to understand when you are understanding region of operation of each and every MOSFET. There is a possibility for switching on both networks for small duration when inputs and outputs are switching. When inputs and outputs are switching, in that duration, there is a possibility for seeing for very small duration, there is a possibility for conducting both pull up and pull down network. That is, while inputs and outputs are switching, there is a possibility for path from supply to ground. That in the duration, there is a small power dissipation, which we name it as a short circuit power, where when inputs and outputs are switching. But when inputs are stable, outputs are stable. There won't be any path from supply to ground. There won't be any path from supply to ground. Understand correctly? There won't be any path from supply to ground when inputs are stable. Why? Only one network will be on. Only one network will be on. That means pull-up network is on, then capacitor charging to VDD, no further charge exchange. And when pull-down network is on, pull-up network is off, then obviously whatever the charge is there in this capacitor will be dissipated. Then there won't be any power dissipation again. Because for stable inputs or static inputs, static outputs, there won't be any power dissipation. That is called static power is eliminated. But when inputs and outputs are switching, there is a possibility for power dissipation. That dissipation is called dynamic power. That is when output is switching from logic 0 to logic 1. So the capacitance is charging to VDD. In that charging, it is drawing current from supply through pull-up network. When it is output is changing from logic 1 to logic 0, the energy stored in the capacitor is dissipated. That is called switching power. And when inputs and outputs are switching, right? When inputs and outputs are switching, there is a possibility for seeing both N-channel MOSFET and P-channel MOSFET for very small duration. For very small duration, like this. When inputs are switching, like this. When inputs are switching like this, and output is switching, for example, inverter, it is like this. For small duration, very small duration, in this duration, there is a possibility for switching on both N-channel MOSFET and P-channel MOSFET. So in that duration also, there will be power dissipation. It is also while inputs and outputs are switching only. That's the reason it is considered as a dynamic power. So supply to ground, there is a possibility for a path when inputs and outputs are switching. So when output is switching from logic 1 to logic 0, logic 0 to logic 1, there is a possibility for dissipating power. Another thing is this one. For small duration, very negligible power, it is static power. Sorry, it is short circuit power. It is short circuit power. So when dynamic power is considered, we have two powers. One is switching power. When output load capacitance is switching, there is a power dissipation, and there is a path from supply to ground for a small duration when inputs are switching, outputs are switching. If you are changing abruptly like this, it is not having any problem. But in reality, it is not possible. It is not possible. Practically, what happens here? Input is also driven by another logic gate. That means the input is getting a capacitance that is charging or discharging through another logic gate. That is also not possible in zero time. So always in this logic gates, there is a capacitance. The capacitance has been charging or discharging. The chargings and dischargings are taking some time. That's what we have considered as a propagation delay. So far, we have discussed about a propagation delay. So chargings and dischargings through on network, it is not in zero time. The time required to charge and discharge, we consider as a propagation delay. In general, we say that 50% input transition to 50% output transition is exactly propagation delay. So in general, 50% input transition to 50% output transition, we say it is a propagation delay. Propagation, 50% input transition, 50% output transition. The time required from this point to this point is considered as a propagation delay. Right? Once we are understanding this construction, and pull-up network is constructed using P-channel MOSFET. Pull-down network is constructed using N-channel MOSFET. Right? Triveni, thank you. Right. So pull-up network is constructed using P-channel MOSFET. Pull-down network is constructed using N-channel MOSFET. Is there any reason for that? See, once again, pull-up network is constructed using P-channel MOSFET. Pull-down network is constructed using N-channel MOSFET. Is there any reason for that? To understand this, whatever I mentioned conditions, you must know. to switch on. Just remember this correctly. I'm going to use this to explain why P-channel MOSFET is constructed, is used in pull-up network construction, why N-channel MOSFET is used in pull-down network construction. So what is the reason behind that? I will explain. Just remember these things: on condition and off condition, on condition and off condition, and also which one is drain, which one is source for N-channel MOSFET and P-channel MOSFET. Which one is drain, which one is source for N-channel MOSFET and P-channel MOSFET, and also what is the on conditions? What is the on conditions? I hope you are clear. So I raised a doubt. What is it here? Pull-up network will be constructed using P-channel MOSFETs. Pull-down network will be constructed using N-channel MOSFET. Pull-up network is constructed using P-channel MOSFET. Pull-down network is constructed using N-channel MOSFET. Right. Logic 1, N-channel MOSFET, and logic 0, P-channel MOSFET. So what, Anand? Yes, Dinesh, 100%. Yes, inputs and outputs are stable, static power. Inputs and outputs are stable, then it is static power. When inputs are switching, there is a possibility for switching outputs also. Then we have a power dissipation, that is called dynamic power. Pranit. Yes, complementary action. It is not there, Vishnu. Again, you are asking. Already I replied for your question. It is not there in your E syllabus. In electrical syllabus, it is not there. If you are interested, you can attend. Already I replied for you. Right? Right? Right. Yes. Static power is removed. Shubham. Excellent. Because there is no path from supply to ground to dissipate the power. Simply, if I consider, right, NMOS logic or resistor transistor logic, resistor transistor RTL, right? This is RTL inverter, resistor transistor logic, or you can use this NPN transistor or whatever be your wish. I'm using a MOSFET in explaining what is it? RTL, resistor transistor logic. Now in this, what is it here? If you are applying a logic 1, if you are applying a logic 1, that is a VDD, then what happens here? It is switching on. It is switching on. That means in on conditions, in on condition, what do you say? I can say there is an on resistance of this MOSFET, and here it is RD, and here it is VDD. So Y must be, as it is on, we are considering output is logic 0. So A, if I say A and Y, if A is 1, output is 0. Correct? Output is 0. Output is 0. There is nothing but output voltage is also not a logic 0, because this MOSFET is offering almost right negligible resistance. Negligible resistance. In that condition, we can say output is logic 0. Output is logic 0. Assuming R on is very negligible. Then what is happening here? There is a path from supply to ground. So inputs are stable. I'm not changing input 1 to 0 or 0 to 1. Input is at logic 1 only. But there is a path from supply to ground. In that condition, so what is it here? VDD square by RD, negligible R on. This power is dissipated continuously. That is called static power. Inputs are not changing. Inputs are stable, static. But there is a power dissipation. That is called static power. That is called static power. Such situation will not be there in this CMOS, because there won't be possibility of path from supply to ground when inputs are stable. Are you understanding? When inputs are switching, there is a possibility for switching outputs. Pranit. So switching power is the energy stored in the capacitor will be dissipated when output is switching from logic 1 to logic 0. Whenever it is becoming logic 1, it is drawn current from supply, that is dissipated through pull down network 1 to 0. 1 to 0. That means output is changing from logic 1 to logic 0. The energy stored the energy stored is dissipated of CV square. Of CV square energy will be dissipated through pull down network. That you are going to study in your devices in depth. Please let me talk with respect to a digital IC. Digital IC. So all these powers and all, you are going to study more and more in your VLSI device. Until that, please hold on. So at this moment, let me cover what is required. Please, right? So much is there which we need to understand about CMOS that we cover in our VLSI, right? Fine. So what we are studying here is there is a possibility for static power in this. The static power is eliminated. Static power is eliminated. Shubham, I don't know. That I cannot see. Shubham, that I cannot see. May or may not. Right, fine. Right, here, right, there is a possibility for static power, but that will be eliminated in this. And what I'm saying here, you need to understand that why N-channel MOSFETs are used in pull-down network, why P-channel MOSFETs are used in pull-up network, why N-channel MOSFETs are used in pull-down network, why P-channel MOSFETs are used in pull-up network. What do we mean by pull-up? Output is pulled to logic 1. What do we mean pull-down network? Output is pulled to logic 0. Once again, so when output is pulled to logic 1, when output is pulled to logic 1 VDD, it is preferable to use P-channel MOSFET. When output is pulled to logic 0, N-channel MOSFET is preferable. Why? We will understand now. So simple concept, very simple concept. Let us see. So if I am using N-channel MOSFET in pull-up network, what happens? Let us see. So pull-down network preferable is what? NMOS. Listen carefully. At pull-up network preferable is what? PMOS. Why we are going to understand now? Why we are going to understand now? So if I use in pull-up network, if I use N-channel MOSFET, let us see what happens. So what is it here? VDD. Let me consider VDD is 5 volts. VTN is a plus 1 volt. VTN is a plus 1 volt. VTP, let me use a minus 1 volt. Understand correctly? Now, here, if I use this N-channel MOSFET in pull-up network, let us see what happens. So in digital IC, if I use N-channel MOSFET in pull-up network, what happens? See, what is happening here? Output node was at 0 initially because I am using N-channel MOSFET in pull-up network. I am assuming, so I am using this N-channel MOSFET in pull-up network, So that means output load capacitance must be charged through N-channel MOSFET, which is used in pull-up network. I am using N-channel MOSFET in pull-up network. Let us see what happens. So to switch on this N-channel MOSFET, what should be applied here? Logic 1. To switch on this N-channel MOSFET, here it must be connected to logic 1. Let me say VDD, which is 5 volts. In our discussion, VDD is 5 volts. Now, which one is gate, which one is drain, which one is source here? This is gate, this is drain, this is source. Why? Higher potential is drain, lower potential is source. Gate is other terminal. Am I right? Are you there? See, this is gate, this is drain, this is source. Right? So gate, drain, source. Why we are confirming that higher potential is drain, lower potential is source. Now, assume output node was at a logic 0. Hold on, Shivalila, please understand. Right. So here, what we are expecting, output was at logic 0. It was at a logic low. Now, this output capacitance is charging through this N-channel MOSFET. Let us see what happens. What is gate to source potential now? Assuming initially it was at logic 0, it is 0 volts. So what is gate to source potential? What is gate to source potential we are getting? 5 minus 0. 5 minus 0, that means 5 volts. It is positive, which is greater than VTN. Can switch on this MOSFET. Understand correctly? Gate to source potential is positive because gate is at 5 volts, source is at 0 volts. Now I am using this N channel MOSFET in pull up network. What may happen? We are understanding. So gate to source potential is 5 volts. Can switch on this N channel MOSFET. There is a conduction between drain and source. Am I right? Now it is conducting. So after some time, let me say it is 1 volt. It is charged to 1 volt. The capacitance is charged to 1 volt. What is gate to source potential now? 5 minus 1, it is 4 volts. Still it is greater than VTN. 1 greater than 1 volt can conduct still. Let me say it is charged to 2 volts. What is gate to source potential now? What is gate to source potential? 5 minus 3 is 2 volts. Still it is greater than 1 volt. Still it is conducting. Then it is charging to 3 volts. Assume that. So what is gate to source potential? 5 minus 3 is 2 volts. Still it is greater than 1 volt. It is conducting. So if it is charged to 4 volts, gate to source potential is how much? 5 minus 4, it is 1 volt. Still it is satisfying on condition. So it can conduct. Assume, for example, assume it is charging to 4.1 volts. It is charging to 4.1 volts. What is gate to source potential? It is now 0.9. For 0.9, it will be off. It will be off. Then output node cannot charge beyond 4 volts. What is VDD? 5 volts. What is logic 1? 5 volts. To pass a logic 1, if I am using N channel MOSFET, it is not getting a strong one. What is strong one? 5 volts. Now we are getting only 4 volts maximum at the output node. So I'm expecting a logic 1 which is strong one, because this may be used as input of another logic gate. So again, it is becoming slow because gate potential is not 5 volts for logic 1 now. It is 4 volts. Further, if you are taking one more stage, it may be becoming 3. It may be becoming some other volts. So logic 1 may be becoming logic 0 after some cycles, after some stages. So it's a problem. It is a problem that should be eliminated. What is it here? Output is not charging to 5 volts when I'm using N channel MOSFET, because beyond 4 volts, if it is charging this capacitance, gate to source potential is becoming lesser than VTN, which can switch off N channel MOSFET. Then what we can say? N channel MOSFET is not passing a strong one to the output. That means if it is passing 5 volts, yes, sir, you can say output is logic 1, it is a strong one. But here we are not able to get 5 volts at output. That is not a strong one. It is getting 4 volts. Still, it may be considered a logic 1 depending on your static discipline we are using in our IC design. But it is not a strong one. It may be considered as a logic 1 up to some extent, up to some stages. It may be working as a logic 1. If you are having more number of stages, it may be becoming slow. It may be becoming logic 0 after some stages. So 4 volts, next stage 4 volts may be becoming 3 volts, 3 volts may be becoming 2 volts, 2 volts may be becoming 1 volt, again it is becoming 0 volts. So finally, what is it here? Logic 1 over a period, if it is propagated, if you are having multi stages, then obviously logic 1 may be treated as logic 0. So it is not considered as a logic 1 for longer duration or longer while. That's the problem. So what we can say here, other possibility. What is it here? This N channel MOSFET, if I use in pull down network, if I use this N channel MOSFET in pull down network, try to understand correctly. Pull down network. Right? What do you mean by this, sir? Already this load capacitance is at VDD, which is 5 volts. Observe correctly. Already it was charged. Now I am using this N channel MOSFET in discharging path. When I am using this N channel MOSFET in discharging path, what happens? Let us try to understand correctly. When I am using N channel MOSFET in pull down network, what happens? I am explaining. So to switch on this N channel MOSFET, this gate must be connected to a logic 1, which is 5 volts. Am I right? Am I right? Logic 1 I am connecting to switch on N channel MOSFET. Already this is output load capacitance was charged to logic 1 because of previous input condition. Output node was charged to logic 1. Now it is used in discharging path. What is that? N channel MOSFET is used in discharging path or pull down network. Pull down network. Then what happens here? So which one is drain, which one is source? Now it is grounded source, it is drain. It is drain. Try to understand correctly. Drain is at higher potential, source is at lower potential. Now gate is connected to logic 1 to switch on N channel MOSFET. Yes. What is gate to source potential now? Source is at 0 volts, gate is at 5 volts. 5 minus 0, it is 5 volts. VGS is 5 volts. Can switch on N channel MOSFET. Then it is conducting. Then what is happening here? Output load capacitance is discharging. Discharging. Understand correctly? Discharging. Discharge to 4 volts. What is gate to source potential? Still it is 5 volts. If it discharge to 3 volts, gate to source potential is how much? 5 volts. Discharge to 2 volts. Gate to source potential is how much? Still it is 5 volts. It is discharged to 1 volt. Gate to source potential is how much? Still it is 5 volts. It is discharged to 0 volts. Not a problem. Gate to source potential still it is 5 volts only. Then what is happening here? Output node capacitance is discharging to ground potential perfectly. That means output is getting a logic 0, which is strong. Which is strong because we are getting a 0 volts there. Whatever we are applying here will be passed to that. See what is happening here. Here you are grounding. It is possible to get that 0 volts at output node. That means a strong 0 is possible. But here weak 1 is possible. It is not a strong one. If you are getting 5 volts at output node capacitance, when I'm using this N channel MOSFET in charging path, then we can say it is passing a strong one. But here it is passing a strong 0. We are able to see 0 volts at output node. Am I right? Am I right? Are you understanding? Are you there? Right. That is Annapurni. Read out. Yes. Yes. So similarly, if I use P channel MOSFET in pull-up network, P channel MOSFET in pull-down network, let us see what happens. Finally, what we are assuming here, what we are understanding here, N channel MOSFET can work effectively in pulling down. In pulling down, output node is pulled to logic 0 perfectly. That is the reason pull-down network is constructed using N channel MOSFET. If I use N channel MOSFET in pull-up network, is having a problem. That's what I discussed. Similarly, let us understand P channel MOSFET functionality. If I use P channel MOSFET in pull-up network, pull-up network, what do you mean by this? Output load capacitance initially was at 0 volts. Now I'm using this P channel MOSFET in charging path. So which one is source? Which one is drain? This is source, this is drain. Why? Source is at higher potential, drain is at lower potential in P channel MOSFET. This is gate, obvious. To switch on this P channel MOSFET, gate must be connected to lower potential, which is logic 0, 0 volts. Am I right? Logic 0 is 0 volts. Am I right? And let me say that VDD is how much? How much? 5 volts. What I'm doing now, P channel MOSFET I am using in charging path, which is pull-up network. So whether it is functioning effectively or not, let us understand. So what must be gate to source potential? Negative, which must be more negative than -1 according to our construction. So VTP is -1 volt means, so gate to source potential must be negative, which must be more negative than -1 to switch on P channel MOSFET. So now gate to source potential of P channel MOSFET is how much? 0 minus 5. It is -5, which is more negative than VTP, which is switching on this side. So P channel MOSFET is helping in charging now because it is conducting. So it is charged to, let me assume that output node capacity is charged to 1 volt. What is gate to source potential? Still -5. Still it is conducting. It is charged to 2 volts. Still gate to source potential is how much? -5. It is charged to 3 volts. Still gate to source potential is -5. It is charged to 4 volts. Still gate to source potential is -5. It is charged to 5 volts. Not a problem, right? Gate to source potential is still -5 only. That means output node capacitance can charge to a logic 1 VDD, which is 5 volts in our discussion, right? So it is able to pass VDD to output node whatever is there on VDD can be passed in digital logic. In digital logic, logic 1 is becoming a strong one at output. Strong one at our output. Am I right? Because it is able to charge up to 5 volts. Because when drain is charging, gate to source potential is not getting affected. So when I'm using P-channel MOSFET in pull-up network, it is able to charge up to VDD. That is logic 1. It is possible to pass a strong one to the output node. To the output node. Am I right? Similarly, if I use P-channel MOSFET in pull-down network, understand correctly. If I use a P-channel MOSFET in pull-down network, what do you mean by pull-down? Already output node is at logic 1, 5 volts. So now I'm using in discharging. In discharging, output load capacitance. Output load capacitance is discharging. Is discharging. Which one is drain? Which one is gate? Which one is source? Here it is gate, here it is source, here it is drain. Because higher potential source, lower potential is drain. Am I right? Now, gate should be connected to logic 0, which is 0 volts to switch on P-channel MOSFET. Yes, I'm connecting. So, gate is connected to logic 0, which is 0 volts, which is 0 volts. So, source, drain, gate. What is gate to source potential? Initially, -5. -5 means more negative than -1 can switch on this MOSFET. That means it is discharging. It is discharged to 4 volts. What is gate to source potential? -5. Still it is source, it is drain. So gate to source potential is how much now? -4. Still it is more negative than -1. So it is conducting still. So it is discharged to 3 volts. What is gate to source potential now? -3. Still it is on. It is conducting. It is conducting. So it is 2 volts. If it is 2 volts, what is gate to source potential now? -2 volts, right? -2 volts. Still it is conducting. Still it is conducting. So what about this? It is charge it to discharge it to 1 volt. What is gate to source potential now? -1 volt. Gate to source potential is -1 volt. Still it is on. For example, if you are taking that it is discharging to 0.9 volts, what is gate to source potential? -0.9. It is not more negative than -1. Then it can switch off. It can switch off because it is not able to discharge beyond 1 volt because gate to source potential is becoming positive than -1. In that condition, trans is going to be off. It cannot discharge. Then 1 volt and beyond that it cannot discharge. That means output is not able to get a strong 0, which is 0 volts here. So when you are using P-channel MOSFET in discharging path, it is not able to pass a strong 0. But here it is able to pass a strong 0. Here, when I'm using N-channel MOSFET in pull-up network, it is not able to pass a VDD to output. It is a weak one. But here, it is able to pass a VDD 5 volts to output. That means NMOS is passing a strong 0. Right? PMOS is passing a strong 1. This is the reason Venkana, what happened? Yes, very good. Now you are understanding PMOS is producing a strong 1 at output, NMOS is producing a strong 0 at output. That is the reason pull-up network is constructed using P-channel MOSFET. Pull-down network is constructed using N-channel MOSFET. Pull-up network is constructed using P-channel MOSFET. Pull-down network is constructed using N-channel MOSFET. Reason behind using P-channel MOSFET in pull-up network, N-channel MOSFET in pull-down network, reason is this. You might have understood correctly. Anyone has any doubts here? Anyone has any doubts here? Anyone has any doubts? You can type in the chat box if you have any doubt. Right? If you are understanding this, let us see how to construct this CMOS circuits. CMOS circuits. Let me take a simple on and off conditions only. Very simple. If I use inverter, this output is Y. Here input is A. If input is A, output is Y. What can be? Let us see. If I say NMOS, this is PMOS. If A and Y, if A is zero, this will be off. Am I right? This MOSFET is off. As it is zero, this P channel MOSFET is on. Then Y is getting VDD, which is logic 1. Anyone has any question? When A is zero, very simple. Everyone knows, sir. Just a quick revision. If A is zero, what is happening here? So this is off, this is on. Y is getting logic 1. If A is 1 and what will be there? Output is 0. Why? If A equals to 1, this is off, this is on. Y is pulled to logic 0, it is 0. That is a CMOS inverter. CMOS inverter. Functionally, what we can say? Y is equals to A bar. Y equals to A bar. Understand correct? NMOS and PMOS. NMOS and PMOS. So I'm using one. Now, let us take a two-input NAND gate. Two-input NAND gate. For constructing NAND, so two switches must be in series in pull-down network. Let me say A and B. And here it is Y. Here it is Y. And these two transistors which are connected to same inputs must be in parallel in pull-up network because dual in nature. Dual in nature. To get complementary function, what we are saying here, those two transistors must be in parallel. It is a VDD. If I say it is A, it is B, then what we get here, check it correctly. Y. So what can we say that A, B, Y? If A, B are 0, 0, what happens here? These two are off, 0, 0. These two are on. Y is connected to VDD, which is logic 1. And if I say 0, 1, if it is 0, it is 1. It is off, this is on. As it is 0, it is 1. This is off, this is on. So it is off, it is on. Then what happens here? Here, what is that here? As it is 0, it is 1. It is on, it is off. As it is on, Y is connected to VDD. So here there is a disconnection, right? Even though A is 0, B is 1, this is on, but this is off. Y is disconnected because of this transistor is off. But A is 0, B is 1, this is on, this is off. So Y is connected to logic 1. So it is a 1. And again, if I connect 1, 0, similar operation. 1, 0, this is on, this is off. As 1, 0, it is off, this is on. 1, 0, this is on. So this will be connected to VDD, which is again logic 1. If I say 1, 1, what is it here? Both are on, these two are off. These two are off, these two are on. Y will be connected to ground, which is 0. And what is this function? AB whole bar. If I want to get AB and function, I need to take again inversion. So if I want to get AB, I have to take inversion. So if I want to implement AB function, first I need to implement AB bar. Then only it is possible to get AB. Directly we cannot get AB. That's the reason it is called complementary CMOS. Whichever the function we want to implement, we are getting that complement. So if I want to implement a function AB, I want to get first AB bar, then I can get AB by using inversion. So complementary CMOS. CMOS means complementary metal oxide semiconductor, but logic family we say that complementary CMOS. Complementary CMOS. Different reasons people say that. So I got this information. What is that here? If I want to implement a function F, I'm getting F bar. So to get F, again I'm taking a complementer. So complementary CMOS. As I'm using that N channel MOSFET and P channel MOSFET, it is CMOS. As I'm getting that expected function complement first, then we are getting that complement of that. So complementary CMOS. That is a NAND function. If I want to implement NOR function, what is here? ORing that means two switches are in parallel, and the same switches which are connected in pull-up network will be in series. Here it is VDD. Then here it is Y. A, B. I'm assuming that you can analyze the why we are getting A plus B whole bar. A plus B whole bar. That you can analyze. That you can analyze. Now let us implement AB plus C whole bar. Complete that implementation. AB plus C whole bar in complementary CMOS. Let us implement AB plus C whole bar in complementary CMOS. Yes, sir. Tomorrow you will be having one more session. That may be last session for digital. One more session. All the EC and IN students, please attend tomorrow also. Yeah, for you, I'll discuss Chakrabarti. Please hold on. If required, I will give that information also. Yes, Dinesh Sai. Yes, I will do that also. Please wait. That will be done later, Surya Teja. Yes. Yes, Padmasri. So first, I need to construct AB. Remember this. Always we go with priority, which we discussed already. So first we construct AB in series. AB in series. First we construct pull down network AB in series and plus C parallel. Plus C parallel. So here it is ground, right? AB, C. Now, what is dual of this AB and series? That AB must be in parallel. AB must be in parallel. So here it must be parallel. Everyone might be knowing this, but a quick revision I'm doing. AB in parallel. And this network is in parallel to C. That means that this network must be in series with C. Here we are getting VDD. Here it is C. No doubt we are getting here AB plus C whole bar. AB plus C whole bar. AB plus C whole bar. Now A plus B and C plus D whole bar. Implement this A plus B and with C plus D whole bar. No problem, you can attend Ajay. There is no restriction. There is no restriction. You can attend. If you are from EE, if you are interested, you can attend. Not a problem. Then what is it here? First, I need to construct a C plus D. Priority order C plus D. Check it correctly. In the parenthesis, C plus D is there. First, implement that. Then ANDing with B. ANDing with D. Then ORing with A. Then parallel. Check it correctly. The priority order which I am following, which I discussed long back, is helping me in constructing this. Yes, sir. First C plus D, ending with B and ORing with E. That's done. In the same order, let us complete it. What is it here? These are in parallel. Those must be in series. Right? After that, this is in series with B. This must be in parallel with B. Right? So after that, this is in parallel with A. That must be in series with the A. This is BD. This is A. This is a CD. This is a B. That's what we are getting. Same. First constructing this and series or parallel. First construct pull down network, exactly dual of this. So A plus B and C plus D whole bar. A plus B and C plus D whole bar. Right? A plus B and C plus D whole bar. Similarly, you can construct a right any logic function which you are preferring. So let us implement A XOR B. A XOR B. Let us implement A XOR B is equals to what we can write? A bar B plus A B bar is equals to what we can write? A bar B bar plus A B whole bar. Right? A bar B bar plus A B whole bar. Any doubt in that? So I am constructing this. What is the advantage also you can understand. Right. So what is it here? It is A, it is B. If I say it is A bar, B bar, then what I can use? A, B. Here it is A bar, B bar. It is VDD, right? It is VDD. Then what we get here? What we get here? AB plus A bar, B bar, whole bar. Directly we are getting A XOR B. Instead of implementing, what is it here? A bar B plus A B bar whole bar and again taking inversion is not required. Directly it is implementing. Directly it is implementing. Another way of implementing is this. What is it here? A bar B bar plus A B can be written as a plus B bar and with A bar plus B whole bar. That is also correct. A plus B bar and with A bar plus B whole bar. A plus B bar and A bar plus B whole bar. A plus B bar and A bar plus B whole bar. You can implement this also. So if it is A XOR B, if it is A XOR B, that you can complete it, is equals to A bar B bar plus AB is equals to what is it? A bar B plus A B bar whole bar. The advantage of complementary CMOS. I'm utilizing that. I'm utilizing that advantage of complementary CMOS. That can be written as a plus B and A bar plus B bar whole bar. We can implement either this or this. Both are using same number of transistors. So here, if it is asked number of transistors, minimum number of transistors, then A bar, B bar also requires 2 plus 2, total 4 transistors. To get A bar, to get B bar, we are using 2 plus 2, 4 transistors, plus 8, it is 12 transistors. That is minimum. Otherwise, if I implement A bar B plus AB bar whole bar, and again inwards, 2 more transistors will be extra. Even though this is also required A bar B bar, but if I'm implementing A bar B plus AB bar whole bar, and again taking inwards, it takes 2 more transistors extra. I am utilizing complementary CMOS advantage. I am utilizing complementary CMOS advantage. I hope you are following. So try to implement this XNOR also. As I mentioned, you can implement either this or this, right? A plus B and A bar plus B bar whole bar also, it is A XNOR B only, because this is what A XOR B only. A XOR B, I can write it as A bar B plus A B bar is equals to A plus B and A bar plus B bar, and A XOR B is equals to, what is it? A bar B bar plus AB is equals to what we can write? A plus B bar and with A bar plus B. You can use any one of these. You can use any one of these. Right? Yes, yes, Dinesh sir. Right. Let me wind up here for today, and see you tomorrow at 7 a.m. So I'll cover the remaining. We'll see some questions on this CMOS. Then we see the remaining, right, concepts which are to be covered. So if you have any doubts, you can raise the hand, sir. Yes, Triveni.
Sir, are you saying CRP questions? Classroom, sir. In CRP questions, are you told 0 to 1, 1 to 2, 2 to 3?
Yeah.
How many flip-flops are used?
Yeah, how many flip-flops required?
I did not understand that, sir. Can you repeat once?
Yeah, let me take that. Just a minute. What is it here is 0 to 1, 1 to 0, 0 to 2, 2 to 0, 0 to 3, again back to 0. If I write states Q1, Q0, Q1, Q0, 0, 0 to what we say, 0, 1, I'm writing this one. Again from 1 to 0 means 0, 1 to, help me, 0, 0, 0, 0, 0 to 1, 0, 1, 0 to 0, 0, 0, 0 to 1, 1, and from 1, 1 to 0, 0, according to the specified. But if you are observing, 0, 0 is having next state 0, 1, 0, 0 is having next state 1, 0, 0, 0 is having next state 1, 1. Which one should I use? All are correct. Because first time 0, 1, next time 1, 0, next time 1, 1. Right? 0, 0, right? Is having next state is 0, 1. 0, 0, next state is having 1, 0. 0, 0, next state is having 1, 1. But which one is correct? All are correct. Can I specify multiple next states for one present state? Not possible. I can specify one present state, one next state. But you know, it is first time, second time, third time. That you know, because you are counting internally in your mind. That should be counted externally. Our system must be in a position to differentiate. These are not same. These are not same. Then what should I do? I use extra bits to differentiate these. What is the 0, 0? Not compulsory to use this only. You can use your own. 1, 1, 1, 0, 0, 1 also you can use. Not a problem. Now, what about this? Simply I use 0, 0 because there is no significance for this. Are they looking same? Listen. Are they looking same now? Are they looking same?
No.
No. Now system is able to differentiate this, right?
Yes, sir.
Now I can specify next state also, right? What can I do? Here it must be there. Here it must be there. Because next state, first state must be matching. Right? If I design this counter, will there be any problem?
how you take only two Q3 Q2 only? Like if I take one,
That is your wish. That is your wish. My intention is these three must be differentiated. To differentiate three possibilities, extra 2 bits required. Triveni,
yes, sir. Yeah, I got
extra 2
it,
bits
sir.
required, because if it is only two possibilities, I can use only 1 bit 0 and 1.
Okay, I got
Here,
it, sir. If
0
I take
0
only
is
Q2
three times.
now,
Triveni, 0 0 is existing three times, sir. But those three
yes,
are
sir.
not same. Those three are not same, that you know. But system doesn't know. System can understand if you are saying that those are different. So if you differentiate those, system can understand. That's what we have done.
Yes, sir. Yeah, got it.
Right?
Yes,
That's the
sir.
logic.
Thanks, sir.
Thank you. Thank you. Pranit Atagara.
Sir, 29F, sir.
What is it?
29F, while calculating minimum number of transistors for A XOR B,
Yes.
sir.
Yes.
Sir, I didn't get it once. Explain, sir.
So here, how many transistors we have used for XOR?
8 transistors we are using.
8
sir.
transistors. But if A bar, B bar is not available,
Use 2 more.
not +2 +4.
How, sir?
To get A bar, one inverter. To get B bar, another inverter, right?
Yes, sir. Okay.
Right? 2 + 2, 4 transistors.
Sir, here the output is AB plus A bar B bar, no, sir?
It is complement, right? AB plus A bar B bar complement.
Okay, sir.
Right? Complement is CMOS.
Yes, sir. Yes, sir.
Understood now?
Yes, sir.
Right. Dinesh sir.
హలో సార్.
Yes, Dinesh.
సార్ ఇప్పుడు మీరు లాస్ట్ లైన్లో ఇప్పుడు ఎక్స్ప్లెయిన్ చేశారు సార్, లైక్ స్టేట్ ఇనిషియలైజేషన్ లైక్ జనరేట్ చేయడానికి సీక్వెన్స్.
అర్థం కాలేదు, మళ్ళీ ఒకసారి. స్టేట్ మినిమైజేషన్
సార్, సీక్వెన్స్ జనరేటర్లో మీరు నెక్స్ట్ స్టేట్, ప్రెసెంట్ స్టేట్, నెక్స్ట్ స్టేట్ ఎగ్జాంపుల్ తీసుకొని ఇంతకుముందు ఎక్స్ప్లెయిన్ చేశారు సార్.
ఏది వన్స్ కాంప్లిమెంటా?
సార్ స్టేట్ అంటే డిఫరెన్స్ ఉండాలని, ప్రతి స్టేట్ డిఫరెంట్ ఉండాలని మీరు Q1 Q2 ఫ్లిప్ ఎన్ని నెంబర్ ఆఫ్ ఫ్లిప్ ఫ్లాప్స్ ఎన్ని ఉంటాయని చెప్పారు సార్.
మళ్ళీ ఒకసారి దినేష్, ఒకసారి మళ్ళీ అడుగు ప్లీజ్.
లైక్ సార్
ఇప్పుడు ఇందాక అమ్మాయి అడిగిన డౌటా?
ఎస్ సార్.
ఓకే, ఏమైంది
సార్ అంటే ఇప్పుడు ప్రతిసారి నేను
ఈ రెడ్ కాకుండా చూసామని ఏమవుతుందంటే 0 0కి నెక్స్ట్ స్టేట్ 0 1 ఉంది, 0 0కి నెక్స్ట్ స్టేట్ 1 0 ఉంది, 0 0కి నెక్స్ట్ స్టేట్ 1 1 ఉంది. అంటే ఒక 0 0 ప్రజెంట్ స్టేట్ కి 0 1 నెక్స్ట్ స్టేట్ ఉంది, 1 0 నెక్స్ట్ స్టేట్ ఉంది, 1 1 నెక్స్ట్ స్టేట్ ఉంది.
లైక్
ఎలా సిస్టమ్ డిఫరెన్షియేట్ చేయగలుగుతుంది చెప్పు?
ఓకే, అంటే స్టేట్ ఇనిషియలైజేషన్ చేసేటప్పుడు ప్రతి స్టేట్ డిఫరెంట్ ఉండాలి.
డిఫరెంట్ గా అంటే డిఫరెంట్ కండిషన్స్ లో డిఫరెంట్ గా అవుట్పుట్ ఇవ్వాలి, కానీ దానికి డిఫరెంట్ కండిషన్స్ తెలియదు.
బట్ ఆ సీక్వెన్స్ ఆ నెంబర్ అనేది ఏదైనా ఉండొచ్చు సార్. లైక్
నేనేం చేస్తున్నా అంటే అవి సేమ్ కాదు అని నీకు తెలుసు, నాకు తెలుసు, సిస్టమ్ తెలియదు కదా. సిస్టమ్ తెలియాలంటే ఒక ఐడి ఇద్దాం. ఏం ఐడి ఇద్దాము? అపెండ్ చేసి ఈ మూడు సేమ్ కావు, మూడింటిని డిఫరెన్షియేట్ చేయాలంటే ఎక్స్ట్రా బిట్ 2 బిట్స్ కావాలి కదా. ఆ 2 బిట్స్ నేను ఇలా తీసుకున్నాను, ఇలాగే తీసుకోవాలని లేదు దినేష్, ఇలాగే తీసుకోవాలని లేదు. నేను ఇంకా ఇలా 1 1 తీసుకుంటాను, ఇక్కడ 1 0 తీసుకుంటాను, ఇక్కడ 0 1 తీసుకుంటాను, నా ప్రాబ్లం ఏం లేదు. ఇలాగే తీసుకోవాలని లేదు, ఒక ఐడి ఇద్దాం. ఇదేమో ఫస్ట్ టైం, ఇదేమో సెకండ్ టైం, థర్డ్ టైం అని ఒక ఐడి ఇచ్చేద్దాం. సిస్టమ్ అర్థం చేసుకుంటుంది. ఎలాగైతే మనం అర్థం చేసుకున్నామో సిస్టమ్ కూడా అర్థం చేసుకోవాలి.
1 అన్నట్టు 0 1 0 0 అంటే సెకండ్ 0 అన్నట్టు.
అది అలా దానికి సిస్టమ్ కి డిఫరెన్షియేట్ చేసేటట్టు ఇచ్చాం.
ఇంకోటి లైక్ 30 క్లాక్ పల్సెస్ అంటే మోడ్ 30 అన్నారు సార్. లైక్
అవును
అది అర్థం కాదు సార్. లైక్ క్లాక్ పల్సెస్ స్టేట్స్ లాగా ఎలా?
ఇప్పుడు ఒక్క నిమిషం, ఏమైంది ఇక్కడ?
30 క్లాక్ పల్సెస్ వచ్చి అంటే మనకి
30 క్లాక్ సైకిల్స్ ఈచ్ సైకిల్ లో కౌంట్ చేయాలి. ఇప్పుడు ఒక్కసారి కనుక అబ్జర్వ్ చేస్తే రెడ్ పడాలి, ఎల్లో పడాలి, గ్రీన్ పడాలి కదా. ఇవన్నీ ఒకసారి అంటే ఒక సైకిల్ అంటే ఈ మొత్తం మళ్ళీ రిపీట్ అవుతానే ఉండాలి. ఇంకా ఒక సైకిల్కి వచ్చేసరికి ఏంటి, రెడ్, ఎల్లో, గ్రీన్ ఒక సైకిల్.
ఎస్ సార్.
అంటే ఒక సైకిల్లో ఎన్ని క్లాక్ సైకిల్స్ కౌంట్ చేస్తుండాలి సిస్టమ్? 30 క్లాక్ సైకిల్స్ కౌంట్ చేయాలి ఒక సైకిల్లో.
ఓకే సార్.
30 క్లాక్ సైకిల్ కౌంట్ చేయాలంటే మాడ్ 30 కౌంటర్ కావాలి అంతే.
ఓకే ఓకే.
ఒక సైకిల్లో ఎన్ని క్లాక్ సైకిల్స్ కౌంట్ చేయాలి? 30 క్లాక్ సైకిల్స్ కౌంట్
ఒక
చేయాలి.
సైకిల్లో అంటే టైం పీరియడ్ సార్. ఒక టైం పీరియడ్
ఇప్పుడు ట్రాఫిక్ సిగ్నల్ ఎలా ఉంటుంది? రెడ్, ఎల్లో, గ్రీన్ వచ్చిన తర్వాత మళ్ళీ రెడ్, ఎల్లో, గ్రీన్ అవుతుందా?
సార్.
అంటే ఇది మళ్ళీ రిపీట్ అవుతానే ఉండాలి కదా.
ఎస్ సార్.
ఒకసారి ఆపరేషన్ ఒక సైకిల్ అన్నాం అనుకో,
ఓకే ఓకే సార్.
ఒక్కసారి ఆపరేషన్ ఒక సైకిల్ అన్నాం అనుకో,
ఎస్ సార్.
ఆ ఒక సైకిల్లో ఎన్ని క్లాక్ సైకిల్స్ కావాలి మనకి?
30 క్లాక్ సైకిల్స్.
30 క్లాక్ సైకిల్. అంటే ప్రతిసారి మనం 30 క్లాక్ సైకిల్స్ కౌంట్ చేస్తూ వెళ్ళాలి. మళ్ళీ రిపీట్ చేయొచ్చు, ఏం కాదు. మళ్ళీ రిపీట్ చేయాలి, ఏం కాదు. మళ్ళీ రిపీట్ చేయాలి.
ఓకే సార్.
అర్థమైనా?
ఓకే ఓకే.
రైట్ దినేష్?
ఓకే రైట్
రైట్.
థ్యాంక్స్.
థ్యాంక్ యూ. మనీషా? ఎస్ మనీషా. Yes, Manisha, are you there? It is not audible. Are you saying anything? Yes, Manisha.
Sir,
Ah.
first frame, sir.
First frame. Okay. Okay.
Sir, yesterday I asked some doubt, sir, on this question.
Yes, yes.
Sir, ఇందులో మనము Q0 అవుట్పుట్ కదా సార్, Q0 అవుట్పుట్ వచ్చి మనము Q1 కి ఇన్పుట్ అంటే FF2 కి ఇన్పుట్ గా ఇస్తాం కదా సార్, అంటే క్లాక్ ఫ్రీక్వెన్సీగా.
అవును.
Q0 తలక అంటే FF0 తలక క్లాక్ ఫ్రీక్వెన్సీ ఒకటి ఉంటుంది కదా సార్, ఏంటంటే టీమిన్ వస్తుంది కదా సార్.
అంటే నువ్వేమనుకుంటున్నావు అంటే ఇలా అనలైజ్ చేస్తారంటున్నావు సపరేట్ దీని నుంచి దీనికి.
అవును సార్. అంటే ఇప్పుడు ఫస్ట్ ఫ్లిప్ ఫ్లాప్ తలక క్లాక్ ఫ్రీక్వెన్సీ వచ్చి
అంటే 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 మనకు తెలియాల్సింది ఏంటంటే అండికేట్ దీని వల్ల కూడా చేంజ్ అవుతుందా లేదా?
yes sir,
దీని వల్ల కూడా చేంజ్ అవుతుంది కదా.
yes sir,
మరి దీని వల్ల కూడా చేంజ్ అవుతుంది. ఇది కూడా స్టేబుల్ రావాలి కదా.
yes sir.
ఇది కూడా స్టేబుల్ రావాలంటే ఎంత టైం పడుతుంది?
and 2 flip flops తలక
2 ఫ్లిప్ ఫ్లాప్స్ అవుట్పుట్ స్టెబిలైజ్ అవుతే అండికేట్ ఇన్పుట్ స్టేబుల్ అవుతుంది కదా.
yes sir.
ఇది ఒకటే కాదు, ఈ రెండు కలిపి ఒక బ్లాక్ కింద తీసుకుంటే ఈ బ్లాక్ ఈ ఫ్లిప్ ఫ్లాప్ సింక్రోనస్ అవుతున్నాయి.
okay sir.
ఈ బ్లాక్ లో అన్ని ఫ్లిప్ ఫ్లాప్స్ ఈ క్లాక్ ఎడ్జ్ తో పని చేయట్లేదు.
okay.
కానీ ఈ బ్లాక్ అవుట్పుట్స్ రెండు ఉన్నాయి, ఒకటి కాదు రెండు ఉన్నాయి. ఈ రెండింటిని యాంటిగేట్ ఇన్పుట్స్ గా తీసుకున్నాం.
okay.
అవునా?
yes sir.
అంటే ఈ రెండు స్టేబుల్ అవడానికి ఒక ఫ్లిప్ ఫ్లాప్ డిలే సరిపోతుందా? సరిపోవట్లేదు. అందుకని ఈ బ్లాక్ అవుట్పుట్ స్టెబిలైజ్ అవ్వాలి అంటే 2 ఫ్లిప్ ఫ్లాప్ డిలేస్ తీసుకున్నాం, అది తీసుకున్నాం.
సార్ అంటే ఫస్ట్ ఫ్లిప్ ఫ్లాప్ తలక టైం టీమిన్ వచ్చి TCK_Q ప్లస్
ఇది లేదనుకో అలాగే చేయొచ్చు. ఈ ఫ్లిప్ ఫ్లాప్ లేదనుకో అలాగే చేయొచ్చు. ఎందుకంటే అండ్ గేట్ కి ఇక్కడ నుంచి ఇక్కడికి కాకుండా ఈ క్లాక్ ఎడ్జ్ నుంచి చూడాలి నువ్వు. ఫ్లిప్ ఫ్లాప్ నుంచి ఫ్లిప్ ఫ్లాప్ కాకుండా క్లాక్ ఎడ్జ్ నుంచి క్లాక్ ఎడ్జ్ వరకు, క్లాక్ ఎడ్జ్ నుంచి క్లాక్ ఎడ్జ్ వరకు. మనీషా
ఓకే సార్,
అర్థమైందా?
13 FF సార్.
ఓకే.
సార్ ఇక్కడ నార్మల్ గా ఇలా ఇంకా మోర్ ఉన్నాయి కదా సార్, కాంబినేషనల్ సర్క్యూట్స్ డ్రా చేసి ఇది
పర్లేదు. చేయడం వల్ల కాంబినేషన్ సర్క్యూట్స్ అని రాయడం వల్ల మనకు వచ్చే కొత్త కాన్సెప్ట్ ఏమీ లేదు. ఒకవేళ కన్వెన్షనల్ క్వశ్చన్ అయితే మంచి మార్కులు వస్తాయి. మనీషా
ఓకే సార్.
అర్థమైందా? ఇక్కడ ఎందుకు వదిలేశానంటే దాంతో మనకి ఇంపార్టెన్స్ లేదు. మనకు ఫైనల్ కన్క్లూజన్ ఏం చెప్పాలి నేను? జెడ్ అనేది Q1 Q2 మీద డిపెండ్ అయి ఉంటుంది అంతే. ఎక్స్ ఏమైనా వేరియేషన్స్ ఉంటే డైరెక్ట్ గా అవుట్పుట్ ఎఫెక్ట్ చేయట్లేదు. ఎక్స్ ఏమైనా వేరియేషన్స్ ఉంటే ఆ వేరియేషన్స్ ఫ్లిప్ ఫ్లాప్ స్టేట్ నెక్స్ట్ క్లాక్ దగ్గర ఎఫెక్ట్ అవుతుంది. ఆ ఫ్లిప్ ఫ్లాప్ అవుట్పుట్స్ ఎఫెక్ట్ అవుతే అప్పుడు జెడ్ చేంజ్ అవుతుంది బికాస్ ఆఫ్ ఎక్స్ వేరియేషన్స్. ఎక్స్ వేరియేషన్స్ ఆర్ నాట్ ఎఫెక్టింగ్ ద జెడ్ అవుట్పుట్ ఇమీడియట్లీ.
ఓకే సార్.
Output is not depending on X directly. X can change the state. State can affect the output. Output is depending only on state. That's what Murray systems. Manisha.
ఓకే సార్.
No.
సార్ నార్మల్ జనరల్ డౌట్ సార్. మీరు చెప్పారు కదా సార్ సిఆర్పిక్యూస్ నుంచి. సిఆర్పిక్యూస్ నుంచి అంటే స్టేట్ ఎఫ్ఎస్ఎం ఉంది కదా సార్, నుంచి 3 వేరియబుల్స్ XYZ వేరియబుల్స్ నుంచి ఒక క్వశ్చన్ చెప్పారు కదా సార్. ఆ క్వశ్చన్ లోని అది స్టేట్ అవుట్పుట్ ఇన్పుట్ మెన్షన్ చేయలేదు కదా సార్. అంటే స్టేట్ అవుట్పుట్ అంటే ఇప్పుడు మోడ్ అనుకోండి వేరియబుల్ బై 0 అని మనం రాసాం సార్.
ఒక నిమిషము, ప్రతి సిస్టమ్ కి అవుట్పుట్స్ ఉండాలని లేదు. ప్రతి సిస్టమ్ కి అవుట్పుట్ ఉండాలని లేదు. అర్థమైనా? అవుట్పుట్ లేదని డౌట్ కదా, అంతే కదా.
ఓకే సార్.
అవుట్పుట్ ఉండాలని గ్యారంటీ ఏం లేదు. అవుట్పుట్ లేకుండా కూడా ఉండొచ్చు
సార్. అంటే ఇచ్చిన క్వశ్చన్ కి మన అంటే ఇచ్చిన క్వశ్చన్ లో మనకి
జస్ట్ అక్కడ మనకి ఏం చేశారంటే అంబిగ్యూటీ ఉందా లేదా చూడమన్నారు అంతే.
అంటే ఇచ్చిన క్వశ్చన్ కి మన రిక్వైర్డ్ డేటా ఉందా లేదా అది చూసుకుని చాలు కదా సార్.
అంతే.
ఓకే సార్.
ఓకే,
థ్యాంక్ యూ సార్.
థ్యాంక్ యూ. Ashish. Ashish.
Good morning, sir.
Very good morning, Ashish.
Yes, sir. There was a question where a counter is counting a sequence 0, 1, then 2, 2 times, 3, 3 times, then up to 15, up to 15 times.
Yes, I can remember.
Yes, I didn't get that, sir. How the number of flip-flops are 8, sir?
Three.
Three,
Right?
sir. Oh, eight, number of flip-flops there were 4, sir. I think 8.
That 4 I explained, right? Just now I explained here.
No, sir. No, sir. That's not my question. Sir, it's counting 0, 1, then 2, 2 times, then 3,
Okay.
3 times.
Okay. The question which I created.
Yes, sir.
0, 1, 2, 2, 3, 3. That means, what should we understand is, people might be understanding that it is counting directly like that. No. What should we understand here is 0 to 1, 4 times, so and so. What is that here? 15 to 15 to 15, 15 times.
Yes.
Again back to this. What happened?
Sir,
0, 0, 0, right? 1, 0, 0, 0, 1. So and so 15 is what? 1, 1, 1. But this 15 is existing how many times, sir?
So it's 15 times.
Right? Then how many times it must be differentiated?
So it
15
should
must be differentiated,
15
right?
times, sir.
15 times it must be differentiated.
Yes, sir.
Then what is that here? To differentiate 15 possibilities, again 4 bits extra, right?
Yes, sir.
Right?
Yes, sir.
Then obviously 4 flip-flops plus 4 flip-flops.
No, sir.
Because here 15 times, sir. 15 times is 15 possibilities, right?
Yes, sir.
So to differentiate 15 possibilities, we need extra 4 bits, sir.
Okay, sir. That's fine. That's okay. But it's initially 2 is it's also counting 2 times. That's
Whichever is maximum deciding, right? Here we have only 2 times, 1 bit is sufficient. Here we have 3 times, 3 bits sufficient. Here we have 4 times, 2 bits sufficient. 5 times, 3 bits. So and so 15 times 4 bits. Maximum we go with, right?
okay, sir. So the maximum we have to choose.
Yes.
Okay, sir.
Yes.
Thank you.
Right. Any more? Right. See you tomorrow.